Hello there, and welcome to the Sleepless Scientist, a quiet place in the cosmos where your thoughts can unwind, and knowledge becomes a soft lullaby for the night. Tonight's journey will take us not just across time, but across existence itself, from the ashes of long-dead stars, through magma oceans and silent ice ages, to the warm firelight of human civilization. We'll drift through galactic collisions, follow the footsteps of single-celled pioneers, and listen to the slow rhythm of tectonic plates shaping continents like ancient hands pressing clay. And we'll wonder, quietly, without urgency, what might come next, after us and beyond us. But, before you settle in and get cozy, I'd love if you could take a moment to like this video and subscribe. Only if you truly find these quiet explorations enjoyable. And when you're ready, leave a comment to let me know where in the world you're listening from and what time it is for you right now. It's always such a joy to see all the places we gather from, each in our own little slice of time. Now, feel free to dim the lights, maybe turn on a fan for a soft background hum, and let's gently begin our journey into deep time together. And if your mind begins to wander, that's perfectly fine. Let it drift. We'll still be here, quietly unfolding the story. Let's start with something simple, yet enormous. You. You're made of atoms. Billions upon billions of them. Every breath you take, every blink, every strand of hair on your head is made from particles that are unimaginably old. The calcium in your bones, the iron in your blood, the oxygen you're breathing in this very moment. They didn't begin on Earth. They began in stars. Not the stars you see twinkling above you on a clear night. Those are still shining. The atoms in your body were forged in the fiery deaths of stars long gone. Supernova exploding in vast clouds of heat and light scattered these elements across the galaxy. And from that cosmic dust, from that debris of destruction, new worlds were born. Earth among them. When you picture Earth today, perhaps you see blue oceans and green forests, clouds casting shadows over mountains, or city lights glowing in the dark. But long before all that, before oxygen, before life, before even a solid crust, Earth was just a possibility. A gathering of dust, a swirl of potential, orbiting a young and temperamental star. The story we're about to explore isn't one of sudden events or loud transformations. It's a tale told in layers of stone, in the drift of continents, in the quiet branching of DNA. It's a story of persistence, of gentle changes, repeated over unthinkable spans of time, and you somehow are here to hear it. So let's ease into it. Imagine the entire 4.5 billion years of Earth's history compressed into a single calendar year. On this scale, Earth forms on January 1st. The first primitive cells don't appear until March. Multicellular life doesn't show up until November. Dinosaurs rule the world in December. And humans? We appear on the last few seconds of December 31st. Not minutes, seconds. Everything we think of as history, the pyramids, the wheel, Shakespeare, space travel, it all happens in a flicker at the very end of this calendar. The rest of the year. That's deep time, and that's where we're going. We'll float through the birth of Earth, through magma seas and comet strikes. We'll watch as life arises in bubbling vents and learns to breathe oxygen, a deadly gas to its ancestors. We'll witness glaciers swallowing continents, volcanoes painting the skies red, and bacteria remaking the atmosphere. Eventually, we'll see forests rise, creatures walk, and minds awaken. But tonight is not about rushing toward the conclusion. It's about the unfolding of everything. Because even now, even lying still in your bed, you are part of that unfolding. You're the latest chapter in a very long story, and perhaps not the last. So, let the story begin. Not with a bang, but with a quiet shimmer in the dark. A whisper of stardust, a soft pulse of gravity drawing clouds of gas together. the universe in its own slow way, preparing to write the first word. Before Earth had oceans, mountains, or even a name, its ingredients were scattered across the cosmos, waiting. They drifted in silence, suspended in cold space, born not in solitude but in fire. Let's go back, not just millions of years or even billions, but nearly to the very beginning, the Big Bang. A moment so dense and hot that space, time and matter unfolded from a singularity smaller than an atom. In the first seconds, the universe expanded faster than the speed of light, not through space, but as space itself. And as it cooled, the first particles emerged, protons, neutrons, electrons, simple and fundamental. Out of this early chaos came hydrogen and helium, the simplest elements in the periodic table. These two, light as breath and common as starlight, filled the vast young universe. Alone, they couldn't build a world like Earth. There was no carbon for life, no oxygen for water, no iron for blood. These things had not yet been made. In a sense, the universe was still waiting for its own ingredients. So, it got to work. Clouds of hydrogen, under their own gravity, began to collapse. And from these swirling cocoons, the first stars were born. These were no gentle suns. They were massive, fast-burning giants, living just a few million years before collapsing under their own weight. When they died spectacularly, in brilliant, catastrophic explosions called supernovae. In that death, something new was created. The pressure and heat of a supernova can forge the heavier elements that hydrogen alone cannot. Oxygen, carbon, iron, elements that you now carry inside you. These atoms didn't gently appear. They were ripped into existence by force, shaped in violence, then scattered like confetti across galaxies. Every iron atom in your blood was born this way, in the heart of a dying star. But even that wasn't enough. For certain rare elements, gold, platinum, uranium, the cosmos needed something more extreme, and so it gave us the collisions of neutron stars. Neutron stars are the collapsed cores of once living giants. A single teaspoon of their matter would weigh more than Mount Everest. When two of these dense remnants spiral together and merge, they release not only bursts of gravitational waves, but also spew out enormous quantities of heavy elements. It is here, in these flickering mergers, that gold is born. It's humbling to think that your wedding ring, or the ancient coins buried beneath your feet, or the uranium deep inside the earth, all originated from the same kind of rare, dazzling event, a collision of stellar corpses in the vacuum of space. These elements didn't remain scattered forever. Over time, gravity worked like a slow, invisible hand, gathering the dust of exploded stars into clouds again, in the quiet arms of spiral galaxies like our Milky Way. Some of those clouds began to collapse, and one, about 4.6 billion years ago, formed the star we now call the Sun. But the Sun didn't come alone. As it ignited, the leftover material around it, gas, ice, rock, metals, began to swirl in a vast spinning disk. And from this protoplanetary disk, tiny grains began to stick to each other. Dust into pebbles, pebbles into boulders, boulders into worlds. One of these worlds, in the warm inner regions of the disk, grew and grew, collecting more mass through a process we call accretion. It was nothing like Earth is now. It was hot, cratered, volatile, and far from stable. But its birth was the quiet beginning of a long and wondrous story. So when we say that Earth is made from stardust, it's not poetic exaggeration. It is chemical truth. The oxygen you breathe, the carbon in your skin, the calcium in your teeth, the potassium in your neurons, they all came from stars. Some of those stars were older than the Milky Way. Some lived and died before Earth was even imagined. You, in a sense, are the continuation of their existence. And that's the strange and gentle part of this story. Death gave birth to life. Not just metaphorically, but literally. The deaths of stars made the ingredients, the silence of space allowed them to cool, and then, somewhere along the winding arm of our galaxy, those ingredients began to gather again, quietly, patiently, until they were ready to become a planet. So tonight, as you lie still, with the darkness outside your window and the quiet hum of distant traffic or wind, remember, your body is built from ancient ash, from atoms older than the mountains, older than the oceans, older than Earth itself, and those atoms are about to become a planet. So now we have our ingredients: gold from a neutron star collision, oxygen from a dying giant, carbon floating in the cosmic dark. But ingredients alone do not make a world. They must be stirred, they must be heated, scattered, and gathered again. And that next part of the story begins in a quiet region of the spiral galaxy, where a cold, massive cloud of gas begins to feel the tug of its own gravity. That cloud, stretching across light years, begins to collapse. Slowly at first, then with a gathering speed. It doesn't fall inward neatly. It begins to spin, and that spin flattens the cloud into a vast rotating disk. At the centre of this disk, gravity builds so intensely that atoms fuse together and a new star ignites in nuclear fire. We call it the Sun. The ignition of the Sun was not a moment of silence. Shockwaves rippled through the disk, pushing and pulling, heating some regions and cooling others. In these regions, clumps of dust began to gather. Tiny grains stuck together, helped by static electricity at first, then by gravity. Over millions of years they grew larger, crashing into each other, sometimes gently, sometimes with explosive results. These growing bodies are called planetesimals, and they are the seeds of planets. Near the young sun, where it was too hot for water and gas to condense, only rock and metal could survive. Here, the terrestrial planets, Mercury, Venus, Earth, and Mars, began to form. Farther out, where it was cooler, gas giants like Jupiter and Saturn gathered enormous envelopes of hydrogen and helium, while icy bodies, the ancestors of comets, waited in the fringes. Earth, in these early days, was nothing like the gentle blue sphere we know now. It was molten, scarred by impacts, and spinning rapidly on its axis. Volcanoes erupted ceaselessly. The air was thick with toxic gases, and its surface was a shifting ocean of lava and stone. And it wasn't alone. Other bodies still roamed the solar system, some small and icy, others large and rocky, many with unstable orbits. One of these bodies, a Mars-sized object that scientists later named Theia, crossed Earth's path in a fateful encounter. The collision that followed was one of the most dramatic events in Earth's history. Theia didn't merely dent the young Earth, it shattered both bodies, ejecting debris high into orbit. Some of that material fell back, becoming part of the Earth again. But some stayed in orbit, slowly gathering, pulled together by gravity, until it formed a companion. Our moon. This moon is unusual. It is large compared to Earth. Its composition matches Earth's mantle more than any other type of rock. And perhaps most importantly, it has never left us. It tugs on Earth's oceans, creating tides. It slows Earth's spin. It helps stabilize our axis, preventing wild shifts in climate. Without it, Earth's story might have unfolded very differently. But the moon brought more than balance. It brought a kind of rhythm, a pattern, a steady beat in the background of deep time, and in that rhythm, Earth began to settle. After the impact, Earth spun rapidly, its days just 5 or 6 hours long. Over time, the moon's gravity pulled at the planet's bulging equator, gradually slowing its spin. The Earth cooled. The magma seas hardened into crust. Water vapour condensed into rain, and for the first time, oceans formed on its surface. And through all of this, Jupiter watched. Not literally, of course, but Jupiter's immense gravity played a quiet role in protecting the inner solar system. Its mass deflected many asteroids and comets, that might otherwise have bombarded Earth into oblivion. In some simulations, without Jupiter, Earth might have been hit hundreds of times more often, enough to prevent stable crusts, stable climates, or even life itself. So in a strange way, we owe our existence to an ancient gas giant 5 times farther from the Sun than we are. It has no solid surface, no oxygen, no life we know of, but it has been our silent guardian since before Earth was truly Earth. By about 4.4 billion years ago, Earth had cooled enough to hold liquid water. The crust was thin, fragile, and still shifting constantly. Volcanoes continued to shape the landscape. The air was thick with carbon dioxide and methane, with barely a trace of the oxygen we now depend on. Sunlight filtered weakly through clouds of ash and haze. But even then, in this harsh and alien world, the stage was nearly set. The ingredients were present. The conditions were harsh, but not impossible. Water flowed. Energy pulsed from volcanoes and the young sun. Minerals accumulated in shallow basins and underwater cracks. And somewhere, among all that activity, something extraordinary was about to happen. Not in a moment, not with a flash or a voice or a sudden spark, but in slow halting steps, chemical reactions repeating, forming patterns, struggling to persist. The Earth, once merely a child of dust and violence, was beginning to warm to life, and so ends the first act. From stardust to rock, from collisions to companions, from chaos to the first quiet pools. By the time Earth had fully formed, it was no quiet planet. It did not begin as a peaceful blue world. It began in chaos. If you could visit Earth in its first 100 million years, you would not recognize it. The surface, still hot from its formation, and the impact that created the moon, was covered in churning seas, not of water, but of molten rock. This was the age of magma oceans, where waves of liquid stone rose and fell like tides, glowing orange under a suffocating toxic sky. The atmosphere, if you could call it that, was thick with carbon dioxide, methane, sulfur and steam. There was no oxygen, no blue sky, no rain. Instead, the air shimmered with heat. Volcanoes, thousands of them, erupted without pause, releasing not only gas but also the first whispers of water vapour. Each eruption added to the dense, churning veil that wrapped around the planet. It was not just internal heat that shaped this world. From beyond, the solar system remained a crowded and dangerous place. Asteroids and icy bodies still roam the paths between planets, many of them left over from the great birth of the system itself. Some slammed into Earth, delivering chaos and energy. But some brought water. Inside these comets and carbon-rich asteroids, molecules of water lay hidden, frozen for eons. When they struck Earth, they released their cargo, not in soft drizzle, but in great bursts of vapour and impact. Bit by bit water arrived, some from within, some from beyond. Steam rose, clouds thickened, the sky darkened and swirled. Then, at last, something changed. As the planet slowly cooled, the relentless heat of the surface began to subside. The magma oceans, still vast, began to harden at the edges. A crust formed, not stable or still, but enough to stand upon. Cracks and ridges spread across the surface like veins in cooling glass. And above, the air reached a tipping point. For the first time in Earth's history, the steam began to condense. It didn't fall gently. It came in torrents, sheets of rain pouring from ash-filled skies, hissing as they hit the still hot ground. The early crust sizzled and cracked under the weight of cooling water. Rivers didn't yet exist, but flows gathered wherever the land dipped. Pools formed in craters, then merged. Over time, rain kept falling, steam kept rising, and the cycle began again. Eventually pools became lakes, lakes joined to seas, and seas expanded into vast early oceans. It's hard to say exactly when Earth's oceans truly stabilised. But by around 4.3 to 4.2 billion years ago, vast bodies of water shimmered under a heavy sky. They would not have looked like the oceans we know today. They were acidic, filled with dissolved minerals and metals from the freshly formed crust. No coral reefs, no fish, no waves gently lapping a sandy shore. Just warm, murky basins beneath thunderous clouds and the dim glow of a young sun. But even in this strange and primitive setting, something essential had happened. Earth had begun to soften, not in danger or heat, but in possibility. This was still a dangerous world. The crust, while present, was thin and unstable. Volcanic eruptions continued without pause, reshaping the surface again and again. The moon, much closer than it is today, tugged hard at the young oceans, creating immense tides that swept across the landscape, carving early paths through stone. These tidal forces stirred the oceans, mixed the chemicals, and may have played a role in life's earliest chemistry. And through it all, the atmosphere thickened. Volcanoes continued to spew out carbon dioxide and methane, building a greenhouse effect that kept the planet warm, even as the sun shone more weakly than it does today. Paradoxically, the poisonous gases were keeping Earth alive, preventing the surface from freezing under a pale young sun. No oxygen yet, no blue sky. But the foundation was there. The crust, fragile but forming. The oceans, hot but persistent. The atmosphere, toxic but insulating. And somewhere, in a crack or pool or bubbling vent, the first whispers of life were beginning to gather. It's easy to think of life as a sudden thing, a spark, a switch, an event. But life does not appear like lightning. It begins like a rhythm, a slow, repeating pattern, a dance of molecules, occasionally stumbling into structure, occasionally surviving just long enough to do it again. And in Earth's newly formed oceans, that dance was about to begin. But for now, in this early chapter, the focus is not yet on life itself, but on the conditions that made it possible. Because even before the first cell emerged, even before the first molecule replicated itself, Earth was preparing. It was cooling, settling, exhaling steam and drinking rain. And in doing so, it became something more than just another rock. It became a world with water. And where there is water, the possibility of life always follows. By now, Earth had cooled enough for oceans to form and remain. The rain no longer hissed against molten stone. Instead, it collected and endured, carving gentle paths across the newly hardened crust, pooling in basins and spreading into vast steaming seas. And beneath those early waters, the planet continued to change, not from above, but from within. The crust that had formed was not uniform or still. It floated in a way on the semi-liquid mantle below. While the surface appeared calm from a distance, it rested on a restless foundation, one that flowed, convected, and whispered in heat. Over time, this movement became more than a geologic curiosity. It became a system. Deep within Earth, heat from radioactive decay and leftover formation energy continued to rise. That heat moved slowly outward, causing the mantle to churn in immense convection cycles. Hot material rising, cooling, and then sinking again. This invisible engine began to fracture the crust above it, dividing it into pieces. These pieces, the first tectonic plates, began to move, not quickly, not dramatically, but enough. Enough to change the face of the planet forever. Plate tectonics is often described as Earth's way of breathing, and though it breathes slowly, measured in centimetres per year, the effects are vast and long-lasting. Plates collided, pushing against each other to raise mountain ranges. They separated, pulling apart to create deep ocean basins and mid-ocean ridges. Some slid beneath others, diving into the mantle in great subduction zones, recycling crust and creating chains of volcanoes. At the boundaries of these plates, energy built up. Sometimes it released as earthquakes, sometimes as eruptions, And in between those dramatic moments, the plates simply drifted, quietly changing the outlines of continents and the depths of seas. Over the next billion years, Earth's surface transformed again and again. Continents rose, eroded, broke apart, and drifted across the globe. These wandering land masses occasionally came together to form supercontinents, massive assemblies of rock and mountain that stretched from pole to pole. The earliest of these supercontinents is called Nuna, or sometimes Columbia, depending on which geologist you ask. It formed around 1.8 to 1.6 billion years ago, though the exact timeline is still being pieced together. After Nuna broke apart, another, Rodinia, took its place, and later, much later, the famous Pangaea would emerge, the one often seen in classroom maps, showing all continents nestled together in one sweeping landmass. Each time these supercontinents formed, they reshaped ocean currents, global temperatures, and weather patterns. They altered the chemistry of the oceans, the height of mountains, and the availability of nutrients in shallow seas. These changes in turn affected life, what kinds could survive, thrive, or fade away. But life wasn't here yet. Not fully. Not in the form we recognise. Still, the stage was being built, slowly and with quiet grandeur. The oceans, meanwhile, became more than just water. They were a kind of laboratory. Rivers washed minerals from land into the seas, where chemical reactions played out across vast surfaces. Elements mixed and settled. Hydrothermal vents on the ocean floor, rich in minerals and heat, belched warm water into the surrounding darkness. These places were teeming with chemistry, rich with opportunity. And while we'll return to the chemistry of life in the next chapter, it's important to pause here and reflect on something quietly magnificent. The surface of our planet moves. It bends, drifts, reshapes itself, not with conscious intention, but with a kind of internal rhythm set in motion by heat and gravity and time. Few planets we know of do this. Mars, for instance, shows little sign of plate tectonics. Venus may have something like it, but without Earth's water to lubricate the crust, it seems to behave differently. Earth is unique, not because it moves, but because it moves in a way that continuously recycles its surface. Old crust is pulled down into the mantle. New crust is formed at ridges. Mountains are raised, then ground down by wind and rain, only to rise again in some new configuration. And through all this, the oceans endure. They rise and fall, they flood and recede, but they remain. The same oceans that began as steaming pools on a toxic world are still here. Transformed, yes, but persistent. In them, water cycles endlessly. From vapour to rain, from river to sea, from ice to cloud and back again. And within that cycle, energy flows, minerals mix, and the seeds of life continue to be nourished. If you've ever stood on the shore and watched waves roll in, you've witnessed the ancient breath of this planet, the pull of the moon, the echo of plate movement, the stirring of heat from below, all converging into a rhythm we now find calming, even ordinary. But there is nothing ordinary about it. To have a world where rock flows, where crust breaks and reforms, where water runs for billions of years, this is rare, precious. Perhaps elsewhere in the universe there are other planets like this. But for now, for us, Earth is our only example, our home in motion. And as those plates shifted and the continents wandered, something extraordinary was beginning to happen. Hidden beneath the surface, nestled in warm cracks and gentle pools. Life, true, fragile, persistent life, was about to begin its quiet song. In a world still young, wrapped in thick clouds and whispering volcanoes, Earth continued to cool. The surface was no longer dominated by lava seas, but by shifting plates, rising continents, and oceans that stretched vast and steaming beneath a dimmer sun. Rain came and went, tides swept over rocky shores, thunder rolled across dark skies filled with methane and carbon dioxide, and somewhere, among this blend of stone and storm, the first murmurs of life began. Not life as you know it. Not even cells. Just chemistry. But chemistry with potential. Imagine a rocky shoreline cut by pools and cracks where water gathers and evaporates again and again. In the day, the sun warms these puddles, causing their contents to concentrate. At night, as the air cools, they condense, mixing with fresh rain or tides. Minerals in the rocks slowly dissolve into the water, feeding a rich chemical soup. Lightning flickers across the sky. Volcanoes rumble in the distance. Energy flows in pulses. And in this rhythm, this quiet, repeating cycle, something remarkable begins to happen. Simple molecules, like fatty acids, begin to assemble. They don't need instruction. Their shape, their chemistry, guides them. In water, they naturally form small spheres, lipid bubbles with a hollow centre. These tiny vesicles aren't alive, but they do something almost magical. They separate an inside from an outside. This is important. Life, as we understand it, begins when chemistry becomes compartmentalized, when a reaction can happen within a boundary, protected from the chaos around it. These early bubbles could hold other molecules, perhaps amino acids, perhaps fragments of RNA, perhaps nothing at all. But they were the start of containers, and containers were the start of cells. Elsewhere, in the dark depths of the ocean floor, another theatre of chemistry was unfolding. At hydrothermal vents, cracks in the crust where hot water spewed into the sea, minerals and gases mixed under high pressure. These vents created towering chimneys made of iron and sulfur, with tiny pores and channels. Inside these mineral structures, steep gradients of temperature and acidity formed natural laboratories, where molecules were constantly pushed and pulled, combined and broken apart. It's possible, though not proven, that life began in places like this. The structures offered protection, energy, and complexity. In their chambers, small molecules might have linked into longer chains, peptides, nucleotides, the precursors to RNA and proteins. And above the sea, on land, geysers and volcanic pools played their own role. These were places of extreme fluctuation, hot, cold, wet, dry. And in those shifting conditions, some molecules behaved in new ways. Wet-dry cycles allowed nucleotides, the building blocks of genetic material, to bond together more easily. When the pool dried, molecules became concentrated, forced into contact. When the rains returned, they separated again, some, carrying new structures with them. Each cycle was a test. Most failed, some broke apart. But a few, just a few, survived long enough to repeat. And repetition, over time, is a kind of persistence. Then, in the presence of sunlight and minerals like clay, some of these strands began to take on functions, not just structure, but activity. Certain RNA molecules, called ribozymes, could help catalyze reactions. They weren't alive, but they were useful. And in nature, usefulness is a step toward endurance. No one knows exactly when it happened, or how many times it tried and failed. Life may have begun not once, but many times. Multiple pathways, multiple origins, most of which vanished without a trace. But eventually one lineage persisted. One combination of molecules became stable enough, repeatable enough, to become more than chemistry. It became biology. And from that point forward, the story changed. But before we move on to that next chapter, it's worth pausing here in the in-between, because this quiet middle ground between rock and life, between chaos and pattern, is perhaps the most astonishing place in Earth's history. Here, nothing is certain, yet everything is becoming possible. The planet had created the conditions: liquid water, energy from the sun and from within, a dynamic crust, cycles of concentration and release, and into those conditions the raw ingredients of life fell. Lightning may have sparked new compounds, Ultraviolet light, while dangerous, also drove chemical reactions, and minerals, humble, ancient minerals, may have guided the earliest formations of order. It's tempting to think of this time as a waiting room, a prelude, but in truth, it was its own long, detailed chapter. Life did not emerge overnight. It took hundreds of millions of years for simple molecules to become something that could grow, replicate and evolve, and even then they were fragile, vulnerable, no cell wall, no defences, just soft structures drifting in a hostile world. But they had one powerful trait: they could change. They could make copies with mistakes, and in those mistakes new forms emerged. So the whispers became murmurs. The chemistry began to loop. Patterns reinforced themselves. The first, delicate threads of heredity took root, not because they were inevitable, but because they were lucky, persistent, and just functional enough to outlast the rest. And all the while, Earth kept breathing. The plates moved, the seas churned, rain continued to fall. Lightning still danced across the sky. It was in every sense a world in motion. And somewhere in a vent or a pool or a sunlit shore, life stirred for the very first time. Somewhere, in the murky shallows or warm mineral vents of a young ocean, the first strands of RNA had begun their work. They assembled clumsily, they copied themselves with errors, and most fell apart before getting anywhere at all. But a few didn't. A few managed to persist, clinging to the fragile bubbles that sheltered them, borrowing energy from the chaotic surroundings, enduring long enough to replicate once more. Over time, those strands grew more stable. Molecules that helped protect or assist replication began to surround them. Bubbles that held more efficient patterns fared better, multiplied more, and with each cycle, with each repetition, nature conducted its slow, accidental experiments. Then, something changed. The transition from RNA to DNA did not happen all at once. It was not a single mutation, nor a planned improvement. But DNA, when it did emerge, offered something new: stability. Its double helix structure, less reactive than RNA, allowed for the storage of longer, more complex instructions. It was harder to damage, better at maintaining the integrity of information over time. It wasn't faster, but it was more reliable, and in the quiet conditions of early Earth, reliability was everything. With DNA, life gained memory. Not conscious memory, of course, but chemical memory. A way to pass down patterns, functions, and features without rewriting them every time. Life could now build on itself. Trial and error became legacy and adaptation. The earlier cells were still incredibly simple. They had no nucleus, no organelles, just a loop of DNA floating in cytoplasm, protected by a fragile membrane. But they could replicate, metabolize, evolve. These were the first prokaryotes, the ancestors of all bacteria and archaea. For nearly 1 billion years they would dominate the planet. They lived everywhere, in the ocean, in rocks, in mud. They fed on sulfur, iron, carbon dioxide. Some used fermentation, others chemosynthesis, drawing energy from chemical reactions instead of light. A few early forms may have evolved in alkaline hydrothermal vents, where steep gradients of temperature and chemistry provided a kind of natural battery. These microbes were extraordinarily small. Trillions of them could fit into a single drop of water, and yet in their simplicity they held astonishing diversity. Some thrived in acidic pools, others in salty lakes. Some preferred scalding temperatures, others the icy darkness beneath early glaciers. Life, even then, was not delicate. It was adaptable, persistent, insistent. Most of these organisms used anaerobic respiration. They lived without oxygen, because there was no oxygen. Instead, they relied on other pathways, using substances like nitrate, sulfate, or methane. These were quiet, efficient systems, honed by countless generations, and although no one could see them, their effects began to build. They changed the composition of oceans, releasing gases, breaking down minerals. They, helped circulate carbon and nitrogen. Their metabolic waste altered the chemistry of their surroundings. They lived and died and decayed, layering the seafloor with organic matter. Some formed stromatolites, layered structures created as microbial mats trapped sediment. These strange rock-like domes can still be found today in places like Shark Bay, Australia. In a world before trees, grass or even animals, they stood as early monuments of life's quiet labour. And through all this, the DNA inside them continued to change. Mutations occurred, most harmful, some beneficial. Occasionally a new pathway appeared. A new protein folded into a shape that could do something useful. Over time, these tiny advantages added up. Prokaryotes diversified. Some lines became more efficient. Others adapted to new niches. Evolution, slow and blind, carried them forward. And perhaps most astonishingly, they did all this without ever forming a brain, a skeleton, or a plan. Because life, at its core, is not about intelligence or beauty or purpose. It is about survival and replication, about preserving instructions long enough to copy them again. And in those instructions, passed down molecule by molecule, Earth's biological future was being written. It's easy to overlook this part of history. There were no towering trees, no flocks of birds, no coral reefs, just water, rock, and life so small you could stand in the middle of it and never know. But it was in this hidden world that the foundations of everything else were laid. Bacteria and archaea are not just ancestors, they are engineers. They created the conditions for the rise of more complex life. They shaped the atmosphere, cycled nutrients, and provided the early scaffolding for ecosystems. Without them, Earth might have remained a lifeless rock with a few interesting chemical quirks. But with them, it became something else entirely. A planet alive. So as we move into the next chapter of the story, a chapter where life starts to change the very sky, it's worth remembering that before lungs filled with air, before eyes blinked open, before anything ever walked or swam or dreamed, the smallest things laid the path, and their path was one of persistence, quiet, invisible, mighty. Somewhere, in the murky shallows or warm mineral vents of a young ocean, the first strands of RNA had begun their work. They assembled clumsily, they copied themselves with errors, and most fell apart before getting anywhere at all. But a few didn't. A few managed to persist, clinging to the fragile bubbles that sheltered them, borrowing energy from the chaotic surroundings, enduring long enough to replicate once more. Over time, those strands grew more stable. Molecules that helped protect or assist replication began to surround them. Bubbles that held more efficient patterns fared better, multiplied more, and with each cycle, with each repetition, nature conducted its slow, accidental experiments. Then, something changed. The transition from RNA to DNA did not happen all at once. It was not a single mutation, nor a planned improvement, but DNA, when it did emerge, offered something new: stability. Its double helix structure, less reactive than RNA, allowed for the storage of longer, more complex instructions. It was harder to damage, better at maintaining the integrity of information over time. It wasn't faster, but it was more reliable. And in the quiet conditions of early Earth, reliability was everything. With DNA, life gained memory. Not conscious memory, of course, but chemical memory. A way to pass down patterns, functions, and features without rewriting them every time. Life could now build on itself. Trial and error became legacy and adaptation. The earlier cells were still incredibly simple. They had no nucleus, no organelles, just a loop of DNA floating in cytoplasm protected by a fragile membrane. But they could replicate, metabolize, evolve. These were the first prokaryotes, the ancestors of all bacteria and archaea. For nearly 1 billion years they would dominate the planet. They lived everywhere, in the ocean, in rocks, in mud. They fed on sulfur, iron, carbon dioxide. Some use fermentation, others chemosynthesis, drawing energy from chemical reactions instead of light. A few early forms may have evolved in alkaline hydrothermal vents, where steep gradients of temperature and chemistry provided a kind of natural battery. These microbes were extraordinarily small. Trillions of them could fit into a single drop of water, and yet, in their simplicity, they held astonishing diversity. Some thrived in acidic pools, others in salty lakes. Some preferred scalding temperatures, others the icy darkness beneath the early glaciers. Life, even then, was not delicate. It was adaptable, persistent, insistent. Most of these organisms used anaerobic respiration. They lived without oxygen, because there was no oxygen. Instead, they relied on other pathways, using substances like nitrate, sulfate, or methane. These were quiet, efficient systems, honed by countless generations. And although no one could see them, their effects began to build. They changed the composition of oceans, releasing gases, breaking down minerals. They helped circulate carbon and nitrogen. Their metabolic waste altered the chemistry of their surroundings. They lived and died and decayed, layering the seafloor with organic matter. Some formed stromatolites, layered structures created as microbial mats trapped sediment. These strange rock-like domes can still be found today in places like Shark Bay, Australia. In a world before trees, grass, or even animals, they stood as early monuments of life's quiet labour. And through all this, the DNA inside them continued to change. Mutations occurred, most harmful, some beneficial. Occasionally a new pathway appeared. A new protein folded into a shape that could do something useful. Over time, these tiny advantages added up. Prokaryotes diversified, some lines became more efficient, others adapted to new niches. Evolution, slow and blind, carried them forward, and perhaps most astonishingly, they did all this without ever forming a brain, a skeleton, or a plan. Because life, at its core, is not about intelligence or beauty or purpose. It is about survival and replication, about preserving instructions long enough to copy them again. And in those instructions, passed down molecule by molecule, Earth's biological future was being written. It's easy to overlook this part of history. There were no towering trees, no flocks of birds, no coral reefs, just water, rock, and life so small you could stand in the middle of it and never know. But it was in this hidden world that the foundations of everything else were laid. Bacteria and archaea are not just ancestors. They are engineers. They created the conditions for the rise of more complex life. They shaped the atmosphere, cycled nutrients, and provided the early scaffolding for ecosystems. Without them, Earth might have remained a lifeless rock with a few interesting chemical quirks. But with them, it became something else entirely, a planet alive. So as we move into the next chapter of the story, a chapter where life starts to change the very sky, it's worth remembering that before lungs filled with air, before eyes blinked open, before anything ever walked or swam or dreamed, the smallest things laid the path. And their path was one of persistence, quiet, invisible, mighty. For a long time, Earth belonged to the anaerobes. Life unfolded quietly in the shadows, deep in the oceans and mud, in the warmth of vents and the stillness of pools untouched by air. These organisms thrived without oxygen. In fact, for many of them, oxygen was a poison, something corrosive, unstable, and dangerous, and for billions of years that danger wasn't present. But then, among these ancient microscopic forms, a new kind of life emerged. It wasn't faster or larger, it wasn't more complex, but it had found a different way to harvest energy. Instead of relying on chemical gradients or the breakdown of minerals, it turned toward light. These were the cyanobacteria, sometimes called blue-green algae. Though they are not algae at all, cyanobacteria developed the remarkable ability to perform oxygenic photosynthesis. That is, they could use sunlight to split water molecules, releasing oxygen as a byproduct. It was not the first time photosynthesis had evolved. Some anaerobic versions had already existed using other compounds, but this was different. This version used water, the most abundant solvent on the planet, and sunlight, the most abundant energy source. At first, it was just a clever adaptation, one more way for microbes to survive, but it carried within it the seed of planetary change. Cyanobacteria spread across the shallow seas, especially where light could reach. They formed mats on rocks, lived in the upper layers of microbial communities, and floated freely through sunlit waters. Each cell, as it absorbed sunlight and processed water, released tiny amounts of oxygen into its surroundings. At first, the oxygen didn't go far. It reacted quickly with iron dissolved in the oceans, oxidizing it into rust. That rust settled onto the seafloor in thin, shimmering layers. These are the banded iron formations we still find today, striped rocks of grey and red that record the slow transformation of the oceans. For millions of years, this oxygen never made it into the air. The oceans acted as a sponge, soaking up the new gas, binding it to iron and other elements. But eventually the sponge became saturated. The iron was used up, and the oxygen began to escape, first into the water itself, then into the atmosphere. This moment is known as the Great Oxygenation Event, and it occurred around 2.4 billion years ago. It was not an explosion. There were no trumpets or waves. Just a gradual, almost unnoticed change. Molecules of oxygen accumulating, molecule by molecule, until the air itself began to shift. For us, that might sound like a good thing. We depend on oxygen. We breathe it every few seconds. Without it, we cannot survive for even a few minutes. But for most life on Earth at the time, oxygen was lethal. It attacked chemical bonds. It disrupted cellular machinery. For the anaerobic microbes that had ruled the planet for eons, the rising oxygen levels were catastrophic. Entire lineages vanished. Some fled underground into deep sediments or thermal vents. Others adapted slowly, evolving enzymes to protect themselves, building defences against this new corrosive atmosphere. The first mass extinction in Earth's history was not caused by impact or fire or ice. It was caused by life itself. One lineage of microbe poisoned the world for almost everything else, and yet in doing so it opened new doors. Because oxygen, though reactive, is also powerful, it enables aerobic respiration, a much more efficient way of extracting energy from food. Organisms that could use it had a clear advantage. They could grow larger, move faster, evolve more complexity. It also allowed for the formation of the ozone layer. Oxygen molecules in the upper atmosphere began to interact with ultraviolet radiation, forming O3, ozone. This thin protective layer blocked the most dangerous solar radiation, allowing life to consider for the first time venturing out of the sea and into the light. But that moment was still far off. For now the world remained microbial. Stromatolites, those layered mats of cyanobacteria and sediment, grew in shallow lagoons, forming structures that waved gently under early tides. Each one, in its stillness, was transforming the air, preparing Earth not just for survival, but for evolution. In a way, this was one of Earth's quietest revolutions. There were no leaders, no declarations, no sudden shifts in landscape, just cells, small and simple, doing what they had evolved to do, absorbing sunlight, releasing oxygen, drifting with the current. And yet, everything changed. The sky became blue. Iron sank from the seas. New pathways emerged. The world began to breathe differently. There's a kind of melancholy to this moment. Progress for some meant extinction for others. The innovation of one group caused the downfall of many. And yet, from that loss, a new chapter began. This would not be the last time Earth's biology reshaped the planet. It would happen again and again, through ice, through fire, through forests and fungi, and eventually humanity. But this was the first time. the first moment life looked outward and altered the air itself. It is a strange thought that every breath you take carries within it the legacy of cyanobacteria. The oxygen in your lungs was made possible by microbes who never knew they were creating the future. They simply lived, and in living, they changed the world. The air was changing. After billions of years under a sky heavy with methane, carbon dioxide and nitrogen, a new gas had begun to assert itself. Invisible, yet profoundly reactive, it seeped into the oceans, into the atmosphere, into the very chemistry of life. Oxygen, a breath of new possibility. For some, a death sentence for many. It's difficult to imagine now, in a world where every inhale brings a rush of this gas to your cells, that oxygen was once a crisis. But for early life, it was just that. A threat not only to existence, but to the entire biological structure that had come before. Anaerobic microbes, the dominant life forms for over 1 billion years, had evolved in a world without oxygen. Their enzymes, their membranes, their metabolic pathways, all depended on chemical balances that oxygen disrupted. When exposed, many of them didn't simply suffer, they broke apart. Oxygen tore into their molecular machinery, creating damaging byproducts, destroying proteins and DNA. The very substance we now associate with vitality was, in those days, an agent of destruction, and yet it hadn't arrived all at once. The Great Oxygenation event was slow by human standards, spanning millions of years, but in evolutionary terms it was abrupt. Life that had adapted over eons to a specific, oxygen-free world now faced a new environment, an oxidizing world, a different Earth. For many lineages it was the end. Whole groups of microbes disappeared from the fossil record, not in a fiery cataclysm or sudden impact, but in silence, extinction without drama. They simply faded, unable to cope with the rising tide of oxygen. But not all perished. Some found refuge, deep in the mud, beneath sediments, inside rock, around hydrothermal vents, places where oxygen could not reach. There, in these dark and quiet spaces, anaerobic life held on. Even today, their descendants persist, in your gut, in lake bottoms, in the deep sea. They are reminders that the old world never entirely vanished, it simply retreated. Meanwhile, other organisms adapted. They evolved enzymes to neutralize oxygen's toxicity, like catalase and superoxide dismutase. They altered their metabolism, embracing the power of aerobic respiration, which offered far more energy per molecule of food than anaerobic methods could. With more energy came the potential for complexity, for larger cells, faster growth and more elaborate structures, and so, as one biological world faded, another began to rise. But the transition was not clean. It was messy, uneven, filled with starts and stops. For millions of years the planet existed in a kind of liminal space, with oxygen levels fluctuating, life experimenting, the atmosphere teetering between past and future. The Earth itself bore the scars of this transformation. In the oceans, the once abundant iron, oxidized by the first waves of oxygen, settled out, blanketing the seafloor in layers of rust. These banded iron formations mark the timeline of change, alternating stripes of red and grey that silently record the planet's evolving chemistry. After the oceans cleared of iron, oxygen had nowhere left to go but up, into the air. There, it began accumulating more freely, and with it came the slow formation of the ozone layer, shielding Earth from ultraviolet radiation. But that too came at a cost. Some of the gases that had once warmed the planet, especially methane, began to break down in the presence of oxygen. Methane is a potent greenhouse gas, far stronger than carbon dioxide. As it was destroyed, Earth's climate began to cool. Eventually, this cooling may have helped trigger one of the most dramatic climate events in Earth's history, Snowball Earth, a time when ice may have covered the entire surface from pole to equator. We'll return to that frozen chapter soon. But for now, we stay here, in the moment when breath became both a weapon and a key. The first mass extinction wasn't flashy. It didn't leave behind craters or bones. It didn't topple forests or drown islands. Instead, it remade the world from the inside out. The chemistry of oceans changed. The structure of cells changed. Even the sky itself, its colour, its clarity, its capacity to shield and shape, changed. And yet, through it all, life continued. Adaptation didn't happen because it was fair. It happened because some lineages, by chance or by chemistry, found a way to endure. Some developed tolerance, others embraced oxygen entirely, and once they did, evolution found new tools to work with. With more energy available, new forms became possible. Larger cells, cells with internal compartments, cells that could do more than just survive. They could specialise, communicate, cooperate. That part of the story is coming next. But for now, it's worth remembering that even the quietest catastrophes can shift the path of everything. A change in air, a different way of breathing, a slow, invisible transformation. The first extinction event wasn't marked by fire or water, it was marked by breath. And from that breath, a new world began to emerge. For a long stretch of Earth's early history, life remained small. Prokaryotes, simple, single-celled organisms without a nucleus, were the only form of life. They lived in oceans, in sediments, in hydrothermal vents. They were everywhere, and they had learned every trick available to them. But there was a limit. A single cell could only do so much alone. Then, around 2 billion years ago, something happened. Not a burst of innovation, but an accident that changed everything. One cell, larger and more flexible than most, engulfed another. This was not unusual. Cells often consumed others for energy. But this time, the smaller cell didn't get digested. Instead, it stayed. It found a place inside the host cell and began to live there. The larger cell provided protection, access to nutrients, a stable environment. In return, the smaller cell did what it had always done, convert energy. But now, instead of just feeding itself, it shared the energy with its host. Over time, what began as an uneasy cohabitation evolved into a true partnership. This was endosymbiosis, one of life's boldest experiments. The engulfed cell was a type of bacterium that specialised in using oxygen to extract energy from food, something prokaryotes had only recently begun to do. Inside its new home, it became more efficient. It shed unnecessary genes. It adapted to its host. And eventually it became what we now call a mitochondrion, the powerhouse of the eukaryotic cell. This wasn't the end of the story. Later, in a separate event, a similar thing happened again, but this time with a different kind of bacterium. This new guest had the power of photosynthesis. Once engulfed, it too was spared digestion, and over time it evolved into the chloroplast, allowing its host cell to turn sunlight into food. These partnerships didn't just make life more efficient, they made life more complex. With internal energy factories, cells could grow larger. They could maintain more structures, carry more genes, store more information. They developed internal compartments, specialised areas for different functions, and they built the first nucleus, a protected vault where their DNA could be copied and repaired with greater accuracy. These were the first eukaryotic cells, our ancestors. Every plant, animal, fungus and protist traces its lineage back to this ancient alliance. Even you, lying quietly as you listen now, carry within each of your trillions of cells tiny mitochondria, remnants of that long-ago guest who never left. But mitochondria gave more than just energy. They introduced something profound, the ability to die on purpose. At first, this may sound strange, but in a world of multicellular cooperation, sometimes death is not a failure but a gift. Cells that are damaged, infected or unneeded can self-destruct, a process called apoptosis. This allows tissues to develop in orderly ways. Fingers form because the cells between them die. Faulty cells are removed before they can become harmful. Mitochondria, with their ancient bacterial chemistry, played a key role in this development. In a sense, life was learning not just how to live, but how to let go when needed. With these tools, energy, compartments, memory, and selective death, eukaryotic cells could do more than just survive. They could cooperate, they could build bodies. But first, they had to thrive as individuals, and they did. For hundreds of millions of years, the oceans were home to diverse single-celled eukaryotes. Some swam with whip-like flagella, some oozed across surfaces, some hunted others, some absorbed light, some formed hard shells, leaving behind microscopic fossils that still drift in the oceans today. And through all of it, the legacy of endosymbiosis remained. Mitochondria powered motion, repair, and growth. Chloroplasts filled the seas with oxygen, and nuclei guarded genomes with care. It is a quiet miracle what cells became. That cooperation, not domination, birthed complexity. That one cell inviting another inside could change the course of life. That inside each of us, still today, are tiny echoes of that first alliance, a host and a guest, living as one. We often think of evolution as competition, survival of the fittest. But here, in the long, slow union of two ancient microbes, we see another truth. Sometimes survival means sharing. Sometimes the greatest leap forward is not a fight, but an embrace. And that embrace would open the door to something even more extraordinary. Multicellular life, where cells not only coexist but cooperate, specialize, and build the bodies of fish, ferns, birds, and eventually us. But that comes next. For now, it is enough to sit with the image of two ancient cells circling each other in the warm oceans of a young world, and realizing that neither must destroy the other, that together they could become more. Life, having learned how to live inside itself, was ready for its next transformation. The leap from single-celled to multicellular life may seem inevitable in hindsight, but it was anything but guaranteed. For hundreds of millions of years, eukaryotic cells flourished on their own, swimming, drifting, feeding, dividing. They had internal compartments, mitochondria for energy, nuclei for storing instructions. They were more versatile than the prokaryotes that came before, but still, they lived alone. Then, in the quiet shallows of Earth's oceans, something changed. Some cells began to stay together after dividing. Instead of drifting apart to become separate individuals, they remained attached. At first, this was likely just a consequence of incomplete division. But slowly, it became something more, something intentional. Cells began to cooperate. They formed clusters, then filaments, then hollow spheres. Some began to take on different roles, one group handling movement, another managing feeding, another offering structural support. This wasn't the rise of animals just yet, but it was the beginning of multicellularity, of life made not of one cell but many, living as one. To do this, cells had to develop new tools. They needed communication, chemical signals that could pass from one cell to another, coordinating activity across the colony. They needed adhesion, proteins that could hold them together tightly without fusing their contents. And eventually, they needed differentiation, the ability to turn specific genes on or off in specific cells so that those cells could become something new. Imagine a hollow ball of cells, floating gently in the sea. Inside, some cells begin to specialize. Some push nutrients inward, others line the outer surface, forming a protective layer. When damage occurs, certain cells step in to repair, and when the group gets too large, it splits. Two coordinated colonies forming from one. This is not mere aggregation, it is the birth of a body. Some of these early multicellular organisms left no fossil trace. They were soft, small, ephemeral, but others left patterns, wrinkled impressions in ancient rocks that suggest colonies of cells growing together, leaving ripples in the mud. Over time, more recognisable forms emerged. Early seaweeds, simple worms, flat disc-shaped creatures without heads or limbs, but with symmetry, layering and flow. From these simple bodies, the principles of animal life would slowly take shape. Symmetry, for example, allowed organisms to move forward in a consistent direction. Polarity, having a front and a back, a top and a bottom, allowed specialization of surfaces. Tissues could form, each made of similar cells working toward a common task. Some could contract, becoming the ancestors of muscle. Others could conduct impulses, early precursors of nerves. Life was learning to compose itself. Cells that had once lived freely now gave up their independence for the sake of something larger. And they were rewarded, not just with safety and numbers, but with the ability to adapt in ways single cells never could. A multicellular creature could grow larger, avoid predators, reach new resources. It could repair itself. It could change form as it grew. And yet, this required trust. If one cell in a colony decided to go its own way, to grow without limits, to ignore signals, it could destroy the whole. So mechanisms evolved to suppress selfishness. Rogue cells were eliminated. Apoptosis, the programmed cell death introduced earlier, became a critical safeguard. Order became not just useful, but necessary. The result was astonishing. Coordination. Not just at the cellular level, but at the level of the organism. Signals passed from one tissue to another. Whole bodies responded to light, temperature, chemical cues. Shapes formed, movements synchronized, and Earth's oceans began to fill, not just with scattered cells, but with beings, organisms made of many parts, growing, sensing, responding. These early creatures were still simple compared to modern animals, but they had crossed a threshold. Evolution now worked not only on the genetics of single cells, but on the design of entire systems: circulation, digestion, reproduction, motion. From this point onward, the tree of life would expand in new and unpredictable directions. It's important to note that multicellularity didn't evolve just once. It arose independently in several lineages, in animals, in plants, in fungi, in certain types of algae. Each time, cells found a way to cooperate, to share resources, to specialize. Each time, life moved from the small to the many, from the individual to the collective, and this movement would shape the world. Because with complexity came not just new forms of life, but new forms of interaction with the environment. Larger organisms could reshape their surroundings, dig into sediments, alter the flow of water, affect nutrient cycles. The biosphere itself began to reflect the behaviour of its most active inhabitants. But before forests rose and predators chased prey, this early period of multicellularity was one of quiet exploration. Life was trying new architectures, tinkering with body plans, practicing coordination, laying the groundwork for the Cambrian explosion yet to come. And throughout it all, each new organism carried within it the memory of what came before. Mitochondria tucked into every cell, DNA folded neatly into nuclei, and the ghost of a single ancient cell that had once decided not to digest its meal, but to let it stay. It is a strange lineage, this one we all share. From that decision came tissues. From tissues came bodies. From bodies came motion. And from motion the planet would never be the same. As multicellular life began its quiet rise in the oceans, the microbial world did not fade. It never would. Even today it is easy to forget, or perhaps easy never to realise at all, that the vast majority of the Earth's biology remains microscopic. The plants and animals we see, the forests and whales and coral reefs, are merely the canopy above a deep-rooted structure that continues to thrive, often unnoticed. Microbes were Earth's first engineers, and in many ways they remain its most influential. From the earliest days of their existence, microbes didn't simply survive within their environment, they shaped it. In colonies and mats, in films across rocks, and in clouds within the water, they began to build what scientists call biofilms, thin, slimy, cooperative layers of cells held together by sticky secretions and shared communication. Biofilms were not just physical shelters, they were chemical communities. Within them, microbes exchanged nutrients, signalled distress, responded to threats. They secreted substances to anchor themselves to surfaces. They coordinated efforts to resist toxins or break down materials. They shifted their behaviour based on population density, engaging in what is now known as quorum sensing, a form of molecular voting that allows microbes to act collectively. These behaviours are not conscious, but they are intelligent, in the most basic and humbling sense of the word. Intelligence, after all, need not look like thought. It can look like pattern recognition, like chemical memory, like response to change. Through these subtle forms of awareness, microbial life became Earth's invisible architects. They built oxygen into the atmosphere, as we saw earlier with cyanobacteria. But they did more. They began cycling elements, carbon, nitrogen, sulfur, turning them from one form to another, making them available for other life forms. They fixed nitrogen from the air, allowing plants in the future to grow. They locked carbon into sediments. They broke down rock, releasing minerals. They created clouds of methane that warmed the young Earth. Everywhere they lived, they altered what they touched. In some cases, they even created new ecosystems, such as microbial mats in shallow waters that supported entire food webs. These mats layered themselves year after year, creating stromatolites, not just fossils, but living structures that are, in some places, still growing today. The idea that something invisible could wield such power is not just fascinating, it is fundamental. For much of Earth's history, microbes were the biosphere, and even now, they are its scaffolding. Every ecosystem on the planet depends on microbial life. In soils, bacteria decompose organic matter, recycling nutrients into forms plants can use. In oceans, planktonic microbes form the base of the food chain, capturing sunlight and carbon, producing much of the oxygen we breathe. Even inside your own body, microbes guide and guard. Your gut hosts trillions of bacteria, helping you digest food, manufacture vitamins, and regulate your immune system. You are, in a way, a colony of cells within a larger colony of microbes, walking ecosystems shaped by ancestors who never had bodies of their own. But long before humans or animals or even plants, microbes were doing something else. They were terraforming. Not through technology or intention, but through sheer persistence, through respiration, fermentation, digestion, through billions upon billions of tiny choices playing out in parallel day after day across every corner of the planet. These quiet processes altered the air, the water, the ground, and in doing so they prepared the way for life to expand. And they did so without central control, without hierarchy, without a plan. That, perhaps, is what makes them most remarkable. A tree grows tall by following a genetic blueprint. An animal navigates by instinct, by memory, by experience. But microbes, they move with the currents, settle where they can, and adjust as needed. Their coordination is emergent, rising from the collective behaviour of many individuals responding to local signals. It is not intelligence as we define it for ourselves, but it is intelligence as nature allows it. And there is one more thing worth noting. Microbes don't only adapt to environments, sometimes they create them. A single bacterium may not alter the pH of its surroundings, but a colony can. 1 million bacteria can shift acidity, salinity, nutrient availability. They can produce protective gels or spread toxins to outcompete rivals. Over time, these actions carve out micro-niches, places within places, worlds within worlds. Even the harshest landscapes, boiling springs, deep-sea vents, acid mines, are not lifeless. They are microbial havens shaped and maintained by organisms that thrive where almost nothing else can. So as we move forward into a world of jellyfish and trilobites, forests and mammals, it is worth pausing to honour these earlier citizens. They were never replaced, never surpassed. They continued and still continue to shape the Earth in every moment. You might imagine the great forces of geology, volcanoes, earthquakes, continents drifting. But underneath, and often above, are the smaller forces. The ones that work not in explosions, but in patterns, in gradients, in tides of chemistry and flows of adaptation. Microbes may not leave monuments, but they have shaped mountains. They may not speak, but they have changed the sky. They are the quiet heartbeat of a living world. There have been times in Earth's long history when the planet grew quiet, not in sound, but in movement. When the seas stilled beneath a blanket of ice, and the wind swept over frozen continents without stirring a single blade of grass. These were the Snowball Earth episodes, moments of global stillness that seem almost impossible to imagine. And yet, the evidence is there. Rocks in tropical latitudes bearing the unmistakable scratches of glaciers, drop stones, chunks of rock carried by ice and dropped into ancient marine sediments, layers of glacial deposits appearing not just near the poles but all across the globe. These signs suggest that, at least twice in Earth's past, the entire planet may have frozen over, wrapped in a shell of ice from equator to pole. The cause? It wasn't just one event, but a cascade of changes. Some scientists suggest that it may have begun with the weathering of newly formed continents near the equator. Rain falling on warm rocks pulls carbon dioxide out of the air, forming weak acids that slowly wear the rock away. This chemical weathering locks carbon into sediments and removes it from the atmosphere, cooling the planet over time. Add to this a sun that was still dimmer than it is today, and Earth became increasingly vulnerable to drops in temperature. But there may have been a cosmic nudge as well. A nearby supernova, exploding somewhere in our galactic neighbourhood, could have bathed Earth in a surge of cosmic radiation. This may sound distant and irrelevant, but that radiation could have increased cloud formation in the atmosphere. More clouds reflecting more sunlight, cooling Earth even further. Once the cooling began, it fed on itself. Ice reflects sunlight far better than land or ocean, so as glaciers spread, the planet absorbed less heat and froze even more. Eventually the oceans began to ice over, not just the surface, but deep, perhaps all the way to the sea floor. Across continents, glaciers marched downward from mountaintops, grinding everything in their path. Rivers froze. The cycle of evaporation and rain nearly stopped. Earth became a world in stasis, quiet, pale, and dangerously still. But even in that stillness, fire remained. Beneath the ice, the planet's interior did not rest. Volcanoes continued to erupt, even if no one saw them. Deep-sea vents still belched heat and minerals into the blackness, and every eruption added carbon dioxide to the atmosphere, slowly and invisibly. There were no forests to absorb it, no rain to wash it away, so the carbon built up. For millions of years, Earth remained locked in ice, but gradually the CO2 levels in the atmosphere grew, each volcanic exhale one more step toward the eventual melt. And then something shifted. At some unknown threshold, perhaps when atmospheric carbon reached 1,000 times its current level, the greenhouse effect took over. The ice began to melt, at first slowly, then all at once. Runoff poured across the continents. Oceans, long starved of fresh input, suddenly flooded with nutrients. Sediments that had lain buried under glaciers broke free. Storms returned. Rain carved new paths into stone. And as the greenhouse warming surged, temperatures didn't just return to normal, they soared. This post-glacial warming may have been one of the most intense in Earth's history. The atmosphere, thick with carbon, trapped heat efficiently. Tropical conditions may have reached the poles. Weathering resumed at a furious pace, drawing carbon back out of the air, but only after thousands of years of chaos. This greenhouse rebound left its mark. We see it in sudden shifts in ocean chemistry, evident in carbon isotope ratios locked in ancient rocks. We see it in the reappearance of carbonate layers, once again deposited in warm, shallow seas. We see it in the traces of life that re-emerge, diversified, energized, and ready. And all of this began with silence, with stillness, with ice. There's something poetic in the idea that Earth's greatest biological expansions were made possible by one of its coldest moments. That stasis, rather than halting progress, prepared the world for its next leap. That fire beneath ice still whispers. It is tempting to think of glaciation as pure destruction, and certainly these deep freezes must have caused extinctions, reshaped coastlines, and stressed even the hardiest forms of life. But they also reset the Earth. They scoured the continents clean. They buried old sediments and exposed new minerals. They paused certain chemical cycles and restarted others with new energy. And when the thaw came, it came into a world ready, nutrient-rich, oxygen-boosted, and bursting with possibility. Soon, cells would begin to swim with purpose, to chase and to flee, to form not just colonies, but creatures. But even in that future, they would carry the memory of the ice, because on Earth, even stillness shapes what moves, even silence leaves echoes, and even when the planet seemed frozen and lifeless, it was quietly breathing, slowly preparing for what would come next. It is easy to imagine that a frozen Earth must have been a dead Earth. But that was never quite true. Even during the most severe glaciations, when ice sheets stretched across the continents, when the oceans may have been sealed beneath kilometres of frozen water, when the sun's light struggled to reach the ocean floor, life did not vanish. It endured, tucked away in cracks and shadows, in heat and darkness, in places overlooked by the ice. At hydrothermal vents, far below the frozen surface, warmth still flowed. These ancient chimneys of black rock belched mineral-rich water into the sea, creating tiny oases in the deep. Here, in complete darkness, chemosynthetic microbes thrived, feeding not on sunlight, but on the energy of chemistry, drawing sustenance from hydrogen sulfide, methane, and iron. These microbial communities had been living in the deep long before ice claimed the surface, and when the freeze came, they barely noticed. For them, the world above had always been distant. Their world was shaped by temperature gradients and mineral plumes, by the gentle convection of seawater and the quiet rhythm of molecules in the dark. But not all life remained hidden in the depths. Even in a Snowball Earth scenario, the freeze was likely not perfect. Some models suggest that thin patches of ice, especially near the equator, may have remained partially open, or at least translucent, allowing just enough sunlight to filter through. Beneath these windows, photosynthetic microbes may have persisted, clinging to survival in shallow, briny pockets where light and water still met. Elsewhere, life adapted in other ways. Microbes found sanctuary in cracks within the ice, where pressure and motion created brine-filled veins. These tiny corridors, invisible to the eye, could act as microhabitats, rich in salts, stable in temperature, shielded from ultraviolet radiation. Within them, microbial films might have grown, exchanging nutrients, communicating through chemical signals, maintaining the slow heartbeat of Earth's biosphere. Some microbes likely entered states of dormancy, halting most of their metabolism, waiting patiently for better conditions. In this suspended animation, cells could survive for years, even centuries, protected from desiccation and damage, relying on tightly folded proteins and repair enzymes to preserve their integrity. And while many lineages must have perished, others endured not just physically, but genetically. Snowball Earth acted as a filter, a stress test for life. Those that survived developed traits that would shape future evolution: resistance to cold, tolerance of low light, ability to recover from extreme stress. These traits, once rare, now became the foundation for what came next. There is something quietly powerful in the idea that evolution continued, even in the stillness. Mutation never stopped. Replication, though slow, went on. Cells continued to divide in the warmth of vents, in the salt, of brine channels, in sediments insulated by snow and time. And with each new generation, natural selection pressed gently forward, sculpting life not through abundance, but through scarcity. When the thaw finally came, those survivors were ready. The sudden influx of meltwater released trapped nutrients into the oceans: phosphorus, nitrogen, iron. Sunlight returned to the shallows. The atmosphere grew warm and rich in carbon dioxide, and from the hidden corners of the planet, microbes surged back into the open. They were not new, but they were changed. They carried with them the resilience of survivors. They had learned to manage stress, to hibernate, to endure, and now, in this post-glacial world, they flourished. Some resumed photosynthesis, others bloomed in nutrient-rich currents, forming the early ancestors of plankton. Some reformed the microbial mats that had blanketed shallow seas. Others became symbionts, joining with larger cells to form complex partnerships. A few had even become predators, feeding on smaller cells in a slow, ancient dance of motion and consumption. But in this moment, what mattered most was that life had returned to the surface. The ocean shimmered again with microbial activity. The sky, once dull, became active with gas exchange. Carbon cycles resumed, oxygen levels ticked upward, and for the first time in a long time, evolution had room to breathe. The glaciation had been a crucible, not a tomb, but a furnace of transformation. What entered it was ancient and familiar. What emerged was newly equipped, subtly different, quietly prepared. It is worth remembering that survival is not always dramatic. Sometimes it means curling into a ball. Sometimes it means slowing down, halting growth, sitting still while the storm passes overhead. Sometimes it means clinging to a crack in the ice, to a pocket of warmth, to a filament of chemical energy in the dark. And yet these small acts of patience are what made everything else possible. The microbial world did not need to change the planet with explosions. It only needed to persist. And by doing so, it preserved the possibility of complexity, of curiosity, of consciousness, even if those things were still far, far in the future. So when we think of great survivors, we need not imagine roaring beasts or clever tools. We might instead imagine a single cell, adrift beneath a frozen sea, gently pulsing, quietly dividing, waiting for the day when the light would return, and when it did, life rose with it. When the ice receded and the world warmed, it was not just a change in temperature, it was a return of potential. After millions of years in a frozen state, the ocean stirred with sunlight and chemistry. Volcanoes had loaded the atmosphere with carbon dioxide. Melting glaciers had washed ancient nutrients into the sea. For the first time in a long time, Earth had everything life needed in abundance: energy, warmth, minerals, space, and life responded. Among the survivors of the Great Freeze were not only hardy microbes and dormant photosynthesizers, there were also more complex cells, eukaryotes, already shaped by endosymbiosis and multicellular cooperation, now poised to take full advantage of a changing world. These cells were no longer simple. Inside them, mitochondria generated energy with remarkable efficiency. Nuclei protected vast amounts of DNA. internal membranes divided tasks across compartments. But perhaps most importantly, these eukaryotic cells had begun to build something new, a cytoskeleton, a flexible internal framework that gave them shape, strength, and movement. It was this innovation that changed the game. With a cytoskeleton, cells could grow larger without collapsing. They could push and pull against their own membranes. They could control their shape, reach out with tiny extensions, and crawl. Some developed flagella, long whip-like appendages powered by internal motors, allowing them to swim through water with intent. No longer were they drifting passively in the currents. They could pursue food, avoid danger, explore. Others began to build pseudopodia, temporary arms of flowing cytoplasm used to engulf prey. This wasn't just digestion, it was predation. For the first time in Earth's history, cells began to hunt. It may seem small, one single cell absorbing another, but in evolutionary terms, this was a revolution. Predation introduced a new kind of relationship between organisms, not just competition for space or nutrients, but active interaction. It drove arms races in size, speed, and defense. It encouraged innovation in sensing, in strategy, in structure. With predators came prey. With prey came the need to hide, to resist, to evolve. Some cells developed hard coatings, others learned to detect chemical trails. A few even began to communicate, releasing signals into the water, warning others of nearby threats, or sharing information about food sources. Complexity was no longer just internal, it was relational. This period in Earth's history, just before the Cambrian explosion, is often described as a biological escalation. The rules of life were shifting. Energy was no longer merely a resource, it was a weapon. Space was no longer just habitat, it was territory. Motion was not just possibility, it was power. Eukaryotic cells, empowered by mitochondria and sculpted by their cytoskeletons, now had the means to respond to this new world. Their flexibility allowed them to experiment with form. Some became elongated swimmers. Others became armoured spheres. Some clumped together in colonies. A few dabbled in multicellularity, combining strengths to survive in hostile conditions. Inside these cells, new systems emerged. Endomembrane networks sorted and packaged proteins. Golgi apparatuses helped transport materials with precision. Lysosomes digested waste, while chloroplasts, in those that had acquired them, converted sunlight into sugar with astonishing efficiency. All of this required coordination. To manage it, cells evolved new regulatory systems. Genes turned on and off with increasing specificity. Signals travelled from the cell membrane to the nucleus and back again. Feedback loops stabilised internal conditions, and slowly cells became not just alive but aware, in their own limited molecular way, of their environment, their energy levels, their neighbours. And then, something even more remarkable began. Some eukaryotic cells didn't just consume smaller ones. They formed new symbiotic relationships, just as their ancestors had with mitochondria and chloroplasts. In some cases, algae took up residence inside larger protists. In others, bacteria nested within animal cells, sharing resources or offering defense. Symbiosis wasn't over, it was evolving. The line between individual and community blurred. Some organisms became chimeras, blends of lineages, each part contributing something useful. This was not theft, it was construction. Life was learning not just to survive, not just to change, but to build from cooperation again and again. The results were strange, diverse, and often fleeting. Many of these early experiments left no fossil record. Their bodies were too soft, their time too brief. But their descendants would come to shape the oceans, the continents, the future. The rise of supercells, large, complex, capable of both autonomy and interaction, laid the groundwork for everything that followed. They became the ancestors of plankton, of seaweeds, of protozoa. They set the stage for animals and plants, for tissues and organs, for nervous systems and bloodstreams. But all of it began here, with a cell deciding not only to live, but to move, not only to consume, but to hunt, not only to divide, but to build. And while the rest of the planet continued its slow geological rhythms, mountains rising, oceans spreading, climates shifting, within the invisible world of water, something was speeding up. Evolution was beginning to gather momentum. The ice had tested life. The thaw had nourished it. And now complexity was finding its rhythm, not in a sudden leap, but in a quiet cellular revolution. The continents you see on a map today are not fixed. They float, slowly, silently on molten rock, drifting across Earth's surface like ancient icebergs on a sea of stone. Over millions of years they collide, merge, stretch apart and begin again. And though these movements are too slow for any one human lifetime to notice, their consequences ripple across deep time. They do not merely shape land, they shape life. Long ago, Earth's land masses were gathered into a supercontinent called Rodinia. It formed over 1 billion years ago, a great sprawling patchwork of crust pressed into a single giant. No forest shaded its interior. No dinosaurs roamed its coasts. It was a world still ruled by microbes and early eukaryotic cells. But the land itself was already preparing the stage for change. Rodinia didn't last. Like all supercontinents, it began to break apart. Beneath the surface, heat built up. Tectonic stress fractured the crust. Rifts opened, and pieces of Rodinia slowly drifted away. As it broke, new coastlines formed. Shallow seas filled the gaps, creating warm, sunlit environments rich in minerals and nutrients. And where new environments appear, evolution stirs. This period of continental breakup encouraged what scientists sometimes call stem evolution, the branching out of early experimental lineages. Organisms explored different ways of being. New body plans arose. Some vanished quickly. Others would one day become ancestors to the great families of life. Continental rifting did more than just make space. It also reshaped ocean currents and climate. Warm equatorial seas circulated more freely. Nutrients were stirred from the depths. Coastal upwelling zones became biological hotspots. Life responded by diversifying. But drift was only half the story. In time, the drifting pieces of Rodinia began to come together again, this time forming a new supercontinent, Pannonia, around 600 million years ago. It didn't last long, barely 60 million years, but during its brief existence, it rearranged Earth's surface once more. It too fractured, and eventually, through a long and tangled series of movements, the supercontinent Pangaea formed. Pangaea, perhaps the most famous of Earth's ancient continents, united nearly all land into one vast landmass. It stretched from pole to pole. Its interior was dry and desert-like. Its coasts were stormy and rich in sediment. But its formation also brought collision, massive crumpling of crust, the lifting of mountains, the folding of seabeds into alpine ridges. These continental collisions brought with them a different kind of evolutionary force, one that pressures life to specialise, where rifting opens space for diversity, mountain building compresses. It isolates species in valleys. It creates new climates at elevation. It drives crown evolution, the refinement and branching of more complex stable lineages. It is in these pressured pockets that new adaptations arise. Fins become limbs, eyes refine vision, lungs adapt to thin air. Tectonics, then, is not just geology. It is a scriptwriter of opportunity and challenge. And the continents, though slow, are never still. Each shift of rock changes wind and weather, salt and sun. Rivers change course. Lakes appear and vanish. Deserts form where once there was forest. And in every crack, in every isolated bay, life tries again. Tinkering, splitting, persisting. Evolution may be guided by genes, but its context is written in stone. And so, with Rodinea's break and Panocia's flicker, with Pangaea's vast reach and eventual demise, the continents became not just passive platforms, but active players in the story of life. This cycle of assembly and breakup, of collision and drift, is known as the supercontinent cycle. It's a rhythm measured not in centuries, but in hundreds of millions of years. And with each beat, life is shaken loose from its patterns, given space to explore or forced to adapt. We often imagine that great change must come from above, from meteors or sunlight, from cosmic accidents or climatic events. And yet, beneath our feet, a quieter force has always been at work. The deep, patient breathing of Earth's mantle, moving continents like chess pieces, creating the theatres in which biology performs. Next, we will turn to what life did on that ever-shifting stage. Because just as the continents moved, so too did the chemistry of the oceans and air. Oxygen levels rose, and with it came a new kind of creature, not just large but visible, not just experimental but enduring. But first it's worth pausing to look down, to imagine the ground beneath you, not as fixed, but as floating, not as a final form, but as a journeying piece of Earth's long and restless mind. The world we know today, its shapes, its edges, its cliffs and coasts, is only a moment. Behind it stretches a dance of stone, slow and constant, shaping everything we are. The continents were moving, the ocean stirring, and the atmosphere, once a haze of gases hostile to complex life, was beginning to shimmer with something new. Oxygen. It hadn't appeared all at once. We've seen how cyanobacteria began releasing it billions of years ago, how it rusted iron in the oceans and triggered Earth's first mass extinction. But even after that great oxygenation, the gas remained in relatively low concentrations. It took time, vast stretches of it, for the balance of sources and sinks to shift, for volcanic outgassing to be overtaken by photosynthetic persistence, for the planet to settle into a new equilibrium. And now, as the continents broke and collided, as erosion carried nutrients into the seas, and as sunlight bathed the shallow coasts of a reorganized Earth, something clicked into place. The oxygen threshold rose high enough to support metabolism on a grand scale. It might seem like a subtle change, just a few more molecules in every breath of water, but the consequences were profound. Higher oxygen levels allowed organisms to extract more energy from the same food. This, in turn, enabled larger bodies, more active lifestyles, and more complex behaviours. Suddenly it became possible to build not just cells but organisms, and almost as if on cue, the oceans began to fill with forms no one had ever seen before. The first were soft-bodied, strange, almost abstract beings known today as the Ediacaran biota, named after the Ediacara Hills in Australia, where their fossils were first discovered. These creatures appeared roughly 635 to 540 million years ago. They were flat, frond-like, often radially symmetrical, and left ghostly impressions in ancient seafloors. We don't know exactly what they were. Some may have been early animals. Others might represent evolutionary experiments, branches that led nowhere, snapshots of life trying out different architectures. They lacked hard parts, so their record is rare and delicate. But they show us something important. Macroscopic life had begun. For the first time, ecosystems were being shaped not just by invisible microbes or drifting cells, but by bodies, organised, visible, moving forms. And then something even more dramatic happened. Around 540 million years ago, life erupted in complexity. In what paleontologists call the Cambrian explosion, nearly all major animal groups, the phyla we still recognise today, appear in the fossil record in a relatively short geological window. The oceans became alive in a new way. Creatures with hard shells, segmented bodies and jointed limbs swam, crawled and burrowed. Some developed eyes, simple at first, but capable of detecting light, shadow and eventually shapes. Others evolved spines, armour and tools for hunting or defence. This was not the beginning of life, nor even the beginning of animals. But it was the moment life became complex and expressive in ways the fossil record could preserve. It was also the moment when ecological roles, predator, prey, grazer, scavenger, crystallised into familiar forms. The food web, as we know it, began to take shape. Why did this happen when it did? It was likely not a single cause, but a convergence. Oxygen was finally abundant enough to sustain high-energy metabolisms. Genetic toolkits, especially Hox genes which controlled body layout, had evolved, allowing animals to diversify and form with small changes in regulation. Environmental pressures from changing oceans and continents created new habitats and niches. And once the arms race of predation began, evolution sped forward in bursts. Those with shells were less likely to be eaten. Those who could burrow escaped detection. Those who could swim outpaced danger. Those with vision had an edge over those who wandered blindly. And so the Cambrian seas were filled with new strategies, sponges filtering water, trilobites scuttling across the seabed, worms tunnelling in mud, jellyfish-like forms pulsing in open water. It is humbling to think that we still carry traces of this event. Your own body plan, head, torso, limbs, symmetry has roots in Cambrian ancestry. The organisation of your nervous system, your digestive tract, your muscles and bones, all echo patterns that first became widespread during this ancient period. And yet, as dazzling as the Cambrian was, it did not erase the world that came before. The microbial realm still thrived in every corner. Stromatolites still layered shallow seas. Plankton still drifted in sunlit currents. And even the soft-bodied creatures of the Ediacaran still left a genetic legacy, their forms absorbed or refined in the next wave of evolution. It was not a replacement, it was a layering. Life did not restart in the Cambrian, it expanded, it grew bolder, brighter, stranger. And in the sediment of that long-lost ocean, the fossils tell the story of creatures with armour and eyes, of shells crushed in the jaws of ancient hunters, of bodies built not just to survive, but to move, to sense, to explore. The oceans were no longer just places of quiet drift. They had become arenas of interaction. And yet, even in the complexity, there was grace. Creatures moved in slow spirals across the seafloor. Filter feeders waved gentle fans into the current. Light trickled down through clear waters, catching the edges of shell and eye, glinting on carapace and fin. For the first time in Earth's story, the world was watching itself. For hundreds of millions of years, the ocean was the only place that knew life. It was where cells first stirred, where bodies formed, and where ecosystems bloomed with endless possibility. But eventually, some of that life began to test the limits of its watery home. Slowly, awkwardly, it turned its gaze to the land. The earliest vertebrates, animals with spines, emerged in the seas during the Paleozoic era. At first, they were jawless and armoured, gliding through the water with mouths adapted for suction and sediment feeding. But the development of jaws, likely evolved from modified gill arches, changed everything. Jaws brought precision and power. Fish could now bite, tear, and hold onto prey. This created new ecological roles, predators, grazers, scavengers, and set off a wave of evolutionary branching. Diversity flourished. Cartilaginous fish, like the ancestors of sharks and rays, glided with speed and efficiency. Bony fish developed more rigid skeletons and buoyancy control, enabling greater manoeuvrability. Among these bony fish, one group held a quiet secret. They had lobed fins, fleshier, more muscular appendages with bone structures inside. These were not the thin, fan-like fins of modern fish. These were proto-limbs. Inside them were bones that, with time and reshaping, would become recognisable as parts of arms and legs. Humerus, radius, ulna. These lobe-finned fish, like Eusthenopteron and later Tiktaalik, were the bridge between two worlds. Tiktaalik, discovered in the Canadian Arctic, lived around 375 million years ago. It had both gills and lungs, fins and wrist-like joints, scales and ribs strong enough to support its weight outside water. Its head could move independently of its body, something fish couldn't do, but land animals would find essential. Tiktaalik likely lived in shallow deltas, where pools formed and dried with the seasons. In such unstable environments, the ability to lift your head to breathe, to prop yourself up, and to crawl to the next pool wasn't just useful, it was survival. And with that, the long transition began. From these early explorers came the first amphibians, vertebrates that could live both in water and on land. They still laid their eggs in water, still had moist skin that needed hydration, but they walked. Their limbs bore weight, their lungs inhaled air, their eyes adjusted to light above the surface. The fossil record gives us glimpses. Acanthostega with limbs but still aquatic habits. Ichthyostega, more robust and suited for land. These creatures did not rush ashore in triumph. They edged forward, tentative, amphibious, half in and half out. But the rewards were vast. On land there was no competition, no predators, no grazers stripping vegetation, no creatures filling the air with movement. It was a world of opportunity, and slowly, amphibians spread across the edges of lakes and rivers into swamps and forests. Their bodies adapted. Bones grew stronger, vertebrae aligned for better support. Limbs angled beneath the body, improving locomotion. Their senses sharpened for air, ears tuned to vibrations through space, eyes to light that refracted without water. And yet, they remained tied to water. Their eggs, soft and jelly-like, needed moisture. Their skin, porous and vulnerable, had to stay damp to function. They were pioneers, but they could not yet sever the tether to the sea. Still, their presence on land reshaped ecosystems. They became both predators and prey, feeding on insects and small invertebrates, providing food for whatever larger creatures would come next. And as plants colonised land, mosses, ferns, early trees, these amphibians created bridges between terrestrial and aquatic worlds. By the late Devonian and into the Carboniferous, these forests grew dense. Swamps spread over equatorial regions. Oxygen levels rose, feeding the metabolism of both animals and plants. Insects grew large, amphibians diversified, and somewhere within this world of lush, wet abundance, evolution prepared its next gift, the amniotic egg. But that story belongs to the next chapter. For now, the journey from water to land remains one of the most profound transitions in Earth's history. It required more than limbs. It demanded a full rearrangement of anatomy, metabolism, behaviour, and reproduction. It was not a leap, it was a gentle climb. 1 foot, 1 breath, 1 heartbeat at a time. For all their strength and ingenuity, the early amphibians remained tethered to the world they came from. Their legs could carry them across forest floors, but their eggs, soft, jelly-like, vulnerable, still had to be laid in water. Without it, life would not begin. Their skin too was a living membrane prone to desiccation. They could breathe air, but they could not forget the sea. Then, somewhere in the swamps of the late Carboniferous, something quiet and revolutionary occurred. A creature laid an egg that didn't need to be dropped into water. This was no ordinary egg. It had a shell, not necessarily hard, but tough and resistant to drying out. Inside was a series of fluid-filled membranes, each with its own task, cushioning the embryo, exchanging gases, collecting waste, feeding growth. This was the amniotic egg, a self-contained world, a portable ocean for life on land. It changed everything. With this single innovation, vertebrates were no longer bound to the edge of ponds or the margins of rivers. They could move inland, into forests, across plains, even into deserts. Their young could develop safely inside a private capsule, sheltered from both drying air and aquatic predators. And with the egg came the reptiles. These early reptiles, descendants of amphibians but newly adapted to the dry world, bore scaly skin that resisted water loss. Their lungs became more efficient. Their posture shifted. They no longer had to drag themselves across the ground like salamanders. They could stand, walk, run. Some grew long and sinuous, slithering through the underbrush. Others developed strong legs and wide jaws, their teeth diversified, sharp for meat, flat for plants. And with the land wide open and full of opportunity, they spread. They became many things. Some remained small and secretive, others grew enormous. By the Permian period, reptilian lineages had diversified into forms both familiar and alien. Synapsids, ancestors of mammals, appeared with differentiated teeth and upright stances. Diapsids, ancestors of modern reptiles and birds, took to every possible habitat. It was a time of experimentation. Some creatures had sail-like backs, perhaps for temperature regulation. Others developed armoured hides. Some burrowed. Some soared across tree branches. Ecosystems became richer, more competitive. Predators sharpened. Herbivores defended. The arms race that had begun in the sea continued now on dry land. And through it all, the amniotic egg remained central, a quiet marvel, a simple invention that enabled all this terrestrial ambition. But Earth, as always, balanced creation with destruction. Around 252 million years ago, at the boundary between the Permian and Triassic periods, the world changed abruptly. Massive volcanic eruptions in what is now Siberia released vast quantities of carbon dioxide and methane. Temperatures soared. Oceans turned acidic and lost oxygen. Rainforests collapsed. Food chains unravelled. This was the Perian-Triassic extinction event, the worst extinction in Earth's history. Over 90% of marine species and 70% of terrestrial species vanished. Entire lineages disappeared. Coral reefs dissolved. Insects, which had flourished in lush carboniferous forests, were decimated. The land grew quiet again, but not empty, because not everything died. Some reptiles survived. So did some synapsids. The ecosystems they inherited were simpler, more open, and in that space new forms would rise. Extinction, harsh though it is, creates ecological vacancies. It resets the board, clears the canopy, allows light to reach the forest floor. Evolution doesn't pause after catastrophe. It adapts to what's left. And so, out of the ashes of the Permian, new dynasties emerged. In the Triassic, reptiles began to reclaim the world. Some grew tall, stood upright and walked on two legs. Some became massive herbivores with long necks. Others developed feathers, though they didn't yet fly. One lineage of synapsids held on quietly, eventually giving rise to mammals. And among the diapsid reptiles, one group began to flourish, in a way that would dominate the next 160 million years. They were the dinosaurs, but that story awaits its own chapter. For now, in this still moment after catastrophe, we pause with the survivors, creatures who endured heat and famine, ash and gas, storms and silence. They carried with them lungs that breathed dry air, skin that shed water, and eggs that cradled new life. They had solved the problem of birth in a dry world, and that solution would carry them, loud and quiet, giant and small, across the next great era. Once the Earth belonged to creatures so vast and strange that their footprints hardened into stone, leaving impressions deeper than memory. For over 160 million years, dinosaurs ruled the continents, not as one species, not even as one shape, but as an astonishing symphony of life, adapted to every role the land, sea and sky could offer. Their reign began after the Permian extinction, when the ecological board had been wiped nearly clean. In the early Triassic, life was sparse and quiet. Reptilian forms crept across baked landscapes, and early synapsids nursed their young in burrows, trying to hold on to what little they had. But among these quiet survivors, a new lineage emerged, one built on strength, posture, and potential. These were the earliest dinosaurs. At first, they were small, bipedal, quick-footed scavengers darting through ferns. But as the Triassic gave way to the Jurassic, they grew and diversified and thrived. Some walked on 2 legs, others on 4. Some became towering herbivores with long necks, like Brachiosaurus and Diplodocus, sweeping treetops with gentle mouths. Others, like Stegosaurus, armoured themselves in plates and spikes. Still others, like Allosaurus, honed the art of predation with teeth and claw. By the Cretaceous, the world was theirs. Dinosaurs had taken over nearly every terrestrial niche. The seas, too, swarmed with ancient reptiles. Mosasaurus, Ichthyosaurus, Plesiosaurus. Though technically not dinosaurs, they shared the world's pageantry. The skies, meanwhile, held the pterosaurs, early flying reptiles with wings of stretched membrane, some no larger than a raven, others spanning the width of a small plane. And then there were the birds. By the late Jurassic, some small feathered dinosaurs, like Archaeopteryx, had taken to the air with fluttering clawed wings. These were not yet the sparrows of today, but they marked a beginning. Feathers, it turns out, may have first evolved for warmth or display, only later becoming tools for flight. All of this happened while the Earth itself was reshaping. The supercontinent Pangaea, once whole, began to fracture. As it split into Laurasia and Gondwana and later into the continents we recognise today, new oceans opened, climates changed, and populations were isolated. Dinosaurs on what would become South America evolved differently than those in what would become Asia or Africa. This continental drift didn't just separate land, it created diversity, forcing evolution to try again in different directions. Flowering plants emerged and began to dominate certain landscapes. Insects co-evolved with them. Pollinators appeared, bringing with them new food webs and ecological niches. Forests shifted, swamps dried, deserts grew, and through it all dinosaurs adapted. They were not static creatures, not the lumbering brutes early imagination once painted. Some were swift, with hollow bones and keen senses. Others were social, herding in groups, guarding their nests. Some may have cared for their young, building nests and staying near. Fossilised footprints suggest family movements, parents and juveniles walking side by side through the soft mud of long-lost plains, and beneath their feet, often beneath their notice, scurried the mammals. Tiny, warm-blooded, mostly nocturnal early mammals emerged during this age as well. Some glided between trees, others burrowed. A few may have laid eggs, like the modern platypus. Others gave live birth. They were not dominant, but they were clever. They evolved in the shadows, feeding at night, hiding from predators too large to notice the quiet rustlings under ferns. Their brains were small but efficient, their senses keen. They couldn't outcompete dinosaurs in size or strength, but they didn't try. Instead, they mastered a different strategy: endurance, flexibility, and patience. It's worth imagining a Mesozoic evening, the sky streaked with the last gold of sunlight, pterosaurs gliding home to rocky cliffs, long-necked sauropods moving like ships through fern groves, the distant call of a predator. In the underbrush, a mouse-like mammal freezes, ears twitching, waiting for the night to come. This world, as rich as it was, felt unshakable. It stretched across ages, continents and climates, from the damp Jurassic forests to the flowering Cretaceous plains. Dinosaurs reigned with elegance and ferocity. And yet, like all things in deep time, it was never permanent. There was no warning, no great pause in their step, no signal in the sky they could have seen coming. But already far above a visitor approached. The end of the dinosaurs was near. But even in their twilight they remained magnificent. Their legacy is written in fossils, in feathers, in the very structure of birds that still soar. Their bones became mountains, their teeth became relics in children's drawers. Their stories echo in bedtime books and museum halls. They were not just giants, they were chapters in Earth's long biography, written in scales and wings and thunder. And their final chapter, though sudden and tragic, would also open the door to another. It began, as so many world-altering moments do, in silence. Somewhere above the blue curve of Earth's sky, a rock, roughly the size of a mountain, had broken loose from its long orbit. It was not evil. It did not aim. It simply fell. For countless millennia, it had wandered the solar system, untouched, unseen, indifferent. And then, with no warning at all, it crossed paths with a living planet. 66 million years ago, the sky over what is now the Yucatan Peninsula of Mexico was torn open. The asteroid struck Earth with a force equivalent to more than 1 billion Hiroshima bombs. In a single instant, the ground erupted. The sea recoiled. Air transformed into fire. A crater over 150 kilometers wide was gouged into the crust. Rocks vaporized. Tsunamis raced across oceans. Forests ignited. The very sky glowed. Particles blasted into the atmosphere formed a shroud that encircled the globe, turning day into dusk, then dusk into darkness. For months, perhaps years, sunlight struggled to reach the surface. Photosynthesis faltered. Plants withered. Food chains collapsed from the bottom up. This was the Cretaceous-Paleogene extinction event, and it was not only the asteroid. Around the same time, on the other side of the world, in what is now India, the Deccan Traps, a vast province of ancient volcanic rock, began to erupt. These eruptions, lasting tens of thousands of years, released vast amounts of carbon dioxide and sulfur into the atmosphere. They heated the planet, acidified the oceans, and compounded the chaos already unfolding. Whether the asteroid triggered this volcanic activity, or whether the two simply coincided, we do not know for sure. But together they reshaped the planet. Nearly 3/4 of all species vanished. The skies, once filled with pterosaurs, fell silent. The seas, once home to ammonites, mosasaurs, and giant marine reptiles, emptied. On land, the towering dinosaurs, every non-avian lineage, disappeared. Tyrannosaurus, Triceratops, Hadrosaurus, all gone. The extinction wasn't instant, but it was swift. Ecosystems collapsed like dominoes, and in their place, for a time, was silence. Ash in the wind, dust on still waters, the echo of giants. But some things endured. Among the survivors were birds, the only dinosaurs that made it through. Their small size, warm blood, and diverse diets gave them resilience. Many could fly to safety. Others nested in hidden places, feeding on seeds and insects in the dim light. Even more quietly in the roots and shadows, mammals endured. They had survived extinctions before. They were adaptable, small, furry, fast-breeding. They ate what remained, seeds, roots, insects, eggs. Some dug into the ground and waited, and when the skies cleared, when the fires died and green began to return to the land, they were still there, blinking in the new light, stepping out into an emptied world. This was not the end of life. It was the end of a chapter. And life, always writing, simply turned the page. From the mammals that survived, new lineages began to radiate. Some grew larger, others specialized. Predators, grazers, climbers, swimmers. With the dinosaurs gone, the niches they had once filled stood vacant, and evolution abhors a vacuum. In the next tens of millions of years, mammals would fill the world, reclaiming the land, conquering the air, even returning to the sea. But in that first dawn, what mattered most was not size or strength or intelligence. It was resilience, the ability to hide, to wait, to eat almost anything, to care for offspring, to adapt without complaint. We sometimes imagine extinction as failure, but survival is not always about winning, it is about enduring. Somewhere in that darkened world, a shrew-like creature, a distant ancestor of primates, nursed its young in a burrow while the ashes of the last Triceratops drifted down outside. It did not know what had ended, it did not plan for what would come, but it was alive, and that was enough. The age of dinosaurs was over, the age of mammals had begun, and Earth, scarred but living, rolled on beneath the stars. The great dinosaurs were gone, their long reign reduced to ash and echoes. And in the quiet that followed, mammals rose, not in triumph, but in persistence. Forests grew again, the air warmed, and in the canopy of trees certain small mammals adapted to a new way of living. They grasped branches with nimble fingers. They developed depth perception to leap from limb to limb. Their young were born helpless, needing care. Bonds formed, eyes met. These were the first primates. For tens of millions of years they lived in the trees, mostly small, mostly quiet, mostly unnoticed. But over time, some lineages grew larger, braver, more curious. In the continent we now call Africa, shifting tectonics and changing climate transformed lush forests into fragmented woodlands and open savannas. Where once you could swing from tree to tree, you now had to walk between them. And that simple change changed everything. To survive in this new landscape, early apes had to stand more upright. They had to scan the horizon, use tools to dig, carry food with their hands. Bipedalism began, not with a decision, but with a series of small advantages. Those who could balance better on two legs travelled farther, carried more, saw danger sooner. But more than bodies, it was brains that began to grow. Not all at once. The evolution of intelligence came in pulses, like slow, thunderous heartbeats echoing across time. The first major burst may have been tied to fire. Somewhere around 2 million years ago, early Homo species began to control flame. Not just for warmth or light, but for cooking. And cooked food changed the brain. It made nutrients easier to absorb. It freed time once spent chewing. It softened roots, tamed meat, made calories more accessible. Brains, being hungry organs, could now be fed more easily. They grew. The second burst came with tools. We had used simple rocks before, sharp edges for slicing, blunt ends for smashing, but now we began to shape them deliberately. Not just tools, but tools for making other tools. Memory stretched farther. Planning deepened. Generations began to share knowledge, not just genes, and with tools came language, or at least the structures that would allow it: vocal control, symbolic thought, social cohesion. We spoke not only in grunts and gestures, but in meanings. The third burst was social. As groups grew larger and more complex, brains adapted not only to hunt or forage, but to navigate relationships. Who had alliances? Who had debts? What stories were told about the stars or the rain or the dead? To be human, it seems, is to know what others believe and what they feel, even when it differs from our own experience. This ability to model other minds is among our most profound traits. It gave rise to empathy, to stories, to cooperation on a vast scale. And so, slowly we emerged. Our species, Homo sapiens, is a recent chapter, only about 300,000 years old. We are not the end of a line, but one of many experiments. Dozens of hominin species walk the earth before us. Homo habilis, Homo erectus, Homo neanderthalensis, Homo floresiensis. Some lasted millions of years, others vanished in a blink. We do not descend from just one pair of humans, but genetic studies have traced lineages through time and found that all living humans share ancestors we now call mitochondrial Eve and Y chromosome Adam. They were not a couple. They lived thousands of years apart, but their genetic lines, passed only through mothers and fathers respectively, are the ones that survived, and this survival was never guaranteed. Our ancestors lived through volcanic winters, droughts, migrations, famines. They walked from Africa into the unknown, spreading across the globe in waves. Some followed coastlines, others braved mountains. Wherever they went, they adapted, and they remembered. They passed down fire, songs, paint on cave walls, tools of stone and bone. Words that no longer exist, stories lost to time but once whispered in the dark. That is what makes us what we are. Not just the size of our brains, but the layers of memory we carry. We do not start from scratch. We inherit imagination. We are, in a sense, the planet learning to look back at itself, to wonder not only how we came to be, but what might come next. And in our cells, in our bones, in the twist of our DNA, we carry the traces of those ancient apes, of forest shadows and firelit eyes, of the long walk across savannah, of the first question ever asked beneath the stars. For hundreds of thousands of years, humans lived as wanderers. We followed herds across shifting grasslands. We hunted with spears carved from stone. We gathered fruits, nuts, roots, and honey. We learned the smells of seasons, the paths of stars, the taste of water in moss. The world was wide, and we knew how to read it with our feet. From our African origins, we began to move outward, first to the Middle East and into Asia, then farther still, into Europe, into the cold tundras of the north, into Australia, and across land bridges that once connected Siberia to the Americas. These journeys did not happen all at once. They unfolded over thousands of generations, shaped by changing climate, curiosity, and sometimes by necessity. We adapted to every place we touched. In the Arctic, we learned to build shelters from snow and skin. In the forests, we carved canoes and hunted in silence. In deserts, we followed oases and knew which plants stored water. Our skin changed colour, our diets shifted, our tools evolved, and through it all we told stories, to remember, to warn, to comfort. But perhaps the most transformative shift in our long walk came not from a destination, but from a decision. Somewhere around 12,000 years ago, in various parts of the world, humans began to plant. It was not a single invention. It happened in the Fertile Crescent, in the valleys of China, in the highlands of the Andes. People began to save seeds, to till soil, to breed plants for taste or yield. They domesticated animals, not just for meat, but for milk, wool, labour. This was the beginning of agriculture. It may not sound dramatic, but it rewrote time. Before farming, time had been measured in footsteps, in seasons, in the movement of herds. But with crops, we began to count differently, from sowing to harvest, from seedling to storage. We settled, built granaries, made calendars, waited. Villages formed, then towns. Populations grew. Division of labour emerged. Not everyone needed to farm, so some people became builders, potters, priests, musicians. Society diversified. Hierarchies began. Property was invented. We built cities. At first, small clusters of stone and mud brick. Jericho, Uruk, Mohenjo-Daro. Then sprawling empires, stitched together by roads, trade, and shared language. Temples rose. Walls were built. Markets filled with spices and fabrics and words from distant places. We learned to write. First in symbols scratched into clay, then in ink on papyrus, then etched in memory and passed from teacher to student. With writing came law, contracts, poetry and prophecy. With it came history, a way not just to live, but to remember how we had lived. We traded goods, but also ideas, gods, dreams, constellations. Stories passed from caravan to caravan, crossing deserts and oceans. Mathematics emerged, astronomy flourished, and in time, so did philosophy. And yet, for all this brilliance, we remained what we had always been. Animals learning to live together, And that perhaps is the hardest part. Because as we built civilizations, we also built boundaries. Nations, flags, armies, borders. We learned to divide as much as to connect. For every monument we raised, we also raised weapons. For every alphabet we inked, we carved maps of conquest. For every medical scroll, there was a battlefield. The Industrial Revolution changed us again. Coal and steam, steel and electricity. We built machines that moved faster than any animal. Engines that dug deeper than any root. We lit the night. We broke distance. We multiplied. Then came the digital revolution. In just a blink of geological time, we began to communicate through satellites, to store knowledge in invisible clouds, to send ideas across oceans in milliseconds. A single thought, typed, shared, seen, can circle the globe while your tea cools beside you. And still, we are adapting. New technologies reshape how we live, how we think, how we love, and how we fear. The internet connects us and confuses us. Cities climb higher, forests fall faster, climates shift, and we argue about the meaning of clouds. We are more than the sum of our progress. We are still the same beings who once sat beside fire, whispering stories into the dark, wondering whether the stars were gods or kin. And those questions have never left us. The world we've built, of cities and satellites, of books and machines, is an extension of our memory. We are not just animals with tools. We are time travellers, using knowledge to live in a world we are always slightly behind in understanding. We carry with us not only our genes, but our inventions, our symbols, our burdens. Each generation inherits not just the earth, but the weight of its ancestors' dreams and decisions. And yet, within that weight is also beauty. We learn, we adapt, we teach. And though we sometimes forget, we also remember, quietly, in songs, in poems, in whispered stories as the fire dims. We are not the end of evolution, we are its newest question. For hundreds of thousands of years, humans lived as wanderers. We followed herds across shifting grasslands. We hunted with spears carved from stone. We gathered fruits, nuts, roots, and honey. We learned the smells of seasons, the paths of stars, the taste of water and moss. The world was wide, and we knew how to read it with our feet. From our African origins, we began to move outward, first to the Middle East and into Asia, then farther still, into Europe, into the cold tundras of the north, into Australia, and across land bridges that once connected Siberia to the Americas. These journeys did not happen all at once. They unfolded over thousands of generations, shaped by changing climate, curiosity, and sometimes by necessity. We adapted to every place we touched. In the Arctic, we learned to build shelters from snow and skin. In the forests, we carved canoes and hunted in silence. In deserts, we followed oases and knew which plants stored water. Our skin changed colour, our diets shifted, our tools evolved. And through it all we told stories, to remember, to warn, to comfort. But perhaps the most transformative shift in our long walk came not from a destination, but from a decision. Somewhere around 12,000 years ago, in various parts of the world, humans began to plant. It was not a single invention. It happened in the Fertile Crescent, in the valleys of China, in the highlands of the Andes. People began to save seeds, to till soil, to breed plants for taste or yield. They domesticated animals, not just for meat, but for milk, wool, labour. This was the beginning of agriculture. It may not sound dramatic, but it rewrote time. Before farming, time had been measured in footsteps, in seasons, in the movement of herds. But with crops, we began to count differently, from sowing to harvest, from seedling to storage. We settled, built granaries, made calendars, waited. Villages formed, then towns. Populations grew, division of labour emerged. Not everyone needed to farm, so some people became builders, potters, priests, musicians. Society diversified, hierarchies began, property was invented, we built cities. At first, small clusters of stone and mud brick, Jericho, Uruk, Mohenjo-Daro, then sprawling empires stitched together by roads, trade and shared language. Temples rose, walls were built, markets filled with spices and fabrics and words from distant places. We learned to write. First in symbols scratched into clay, then in ink on papyrus, then etched in memory and passed from teacher to student. With writing came law, contracts, poetry and prophecy. With it came history, a way not just to live, but to remember how we had lived. We traded goods, but also ideas, gods, dreams, constellations. Stories passed from caravan to caravan, crossing deserts and oceans. Mathematics emerged, astronomy flourished, and in time so did philosophy. And yet, for all this brilliance, we remained what we had always been, animals learning to live together. And that perhaps is the hardest part, because as we built civilizations, we also built boundaries, nations, flags, armies, borders. We learned to divide as much as to connect. For every monument we raised, we also raised weapons. For every alphabet we inked, we carved maps of conquest. For every medical scroll, there was a battlefield. The Industrial Revolution changed us again. Coal and steam, steel and electricity. We built machines that moved faster than any animal, engines that dug deeper than any root. We lit the night. We broke distance. We multiplied. Then came the digital revolution. In just a blink of geological time, we began to communicate through satellites, to store knowledge in invisible clouds, to send ideas across oceans in milliseconds. A single thought, typed, shared, seen, can circle the globe while your tea cools beside you. And still, we are adapting. New technologies reshape how we live, how we think, how we love, and how we fear. The internet connects us and confuses us. Cities climb higher, forests fall faster, climates shift, and we argue about the meaning of clouds. We are more than the sum of our progress. We are still the same beings who once sat beside fire, whispering stories into the dark, wondering whether the stars were gods or kin. And those questions have never left us. The world we've built, of cities and satellites, of books and machines, is an extension of our memory. We are not just animals with tools. We are time travellers, using knowledge to live in a world we're always slightly behind in understanding. We carry with us not only our genes, but our inventions, our symbols, our burdens. Each generation inherits not just the earth, but the weight of its ancestors' dreams and decisions. And yet, within that weight is also beauty. We learn, we adapt, we teach. And though we sometimes forget, we also remember, quietly, in songs, in poems, in whispered stories as the fire dims. We are not the end of evolution, we are its newest question. When you look in the mirror, what you see is skin and eyes, limbs and thought, a human face shaped by evolution, culture and memory. But what you don't see, what no mirror shows, is that much of what makes you human is not human at all. You're not one organism, you're many. Inside your gut, across your skin, in your lungs and even your mouth, live trillions of microscopic creatures, bacteria, viruses, archaea, and fungi. Collectively, they are known as your microbiome. They are not invaders, they are residents, and they have been with you since the moment you were born. In fact, even that moment, the act of birth, is a microbial exchange. As you pass through the birth canal, your body is seeded with bacteria from your mother. If you are born through other means, your first microbes may come from skin, milk, or hospital air. But however it begins, your microbiome begins to take root within hours, and it stays with you for life. These microbes are not passengers, they are collaborators. In your digestive tract, they help break down fibres your own enzymes cannot. They produce vitamins. They train your immune system, teaching it what to fight, what to tolerate. They help form the lining of your intestines, preventing harmful invaders from crossing into your bloodstream. But their influence goes even deeper. Modern science has uncovered a remarkable connection between the gut and the brain. Your microbiome can influence the production of neurotransmitters, like serotonin and dopamine, which shape your mood, your focus, your sense of safety. This is sometimes called the gut-brain axis, a delicate feedback loop where microbes can affect anxiety, memory, even how you respond to stress. Experiments in mice have shown that changing gut bacteria can change behaviour, and though humans are far more complex, the idea remains. How we feel is not only shaped by what we think, but by what lives inside us. It's not just the brain. The microbiome may also influence metabolism, inflammation, even how we respond to medications. In many ways, these microscopic communities are like organs we didn't know we had. Dynamic, adaptive, essential. And like all ecosystems, they can be harmed. Modern life has altered our inner worlds. Antibiotics, while life-saving, can wipe out beneficial microbes. Diets high in sugar and low in fibre leave some bacterial populations starving. Lack of outdoor exposure, over-sanitization, and stress can narrow microbial diversity. Sometimes, without even noticing, we drift away from the balance our ancestors lived in. Because for most of human history, our microbiomes were shaped by soil, by animals, by food pulled from the earth and eaten without being stripped of every microbe. We lived with nature not just around us, but within us. We were covered in it, fed by it, composed of it. Even now, traditional lifestyles, hunter-gatherer diets, time spent outdoors, varied exposure to microbes, often show greater gut diversity than urbanized populations. And while more diversity isn't always better, it often correlates with resilience against allergies, autoimmune diseases, even certain mental health challenges. But this isn't a cautionary tale, it's an invitation. Because your microbiome is not fixed, it changes, daily, weekly, with age, with what you eat, how you sleep, whether you hug someone or spend time in nature. It is, in many ways, a record of how you live, a diary of invisible allies. And the more we learn, the more we realise we are not single creatures. We are walking, breathing ecosystems. Each of us is a rainforest of cells and signals, of human tissue and microbial whisperers. You're not alone in your thoughts or your feelings. Tiny companions accompany you, shaping digestion, sharpening memory, tuning the immune symphony that protects you from harm. In a very real way, we evolve together. As mammals emerge from burrows after the Great Extinction, their guts were already home to these symbiotic partners. As primates climbed trees and nursed their young, as early humans foraged and gathered, cooked and fermented, laughed and mourned, the microbiome came with us. It helped us adapt, and we helped it spread. Even now, when we travel, move, or fall in love, we share microbes. We shape each other biologically. Our homes begin to resemble our microbial makeup. Our pets influence our guts. Our relationships leave biochemical traces inside us. The poet Rainer Maria Rilke once wrote that we are bees of the invisible. It turns out we're also gardens of the invisible, tended not by hands but by breath, food, contact and time. So when you next feel alone, remember, you are many. Not just in story or in ancestry, but in biology. You're a chorus of life, some human, some not, but all yours. It's strange to realise that the thin breath of air we call atmosphere, just a few dozen kilometres thick, holds the fate of nearly everything we know. It's even stranger to realise that in only a few generations we've changed it. For nearly all of Earth's history, climate has shifted because of natural forces, volcanic eruptions, orbital wobbles, supernovae and tectonic rearrangements. But in this brief moment, the driver has become us. With the Industrial Revolution, We unlock the energy of ancient sunlight, fossil fuels, compressed remnants of long-dead forests and plankton, stored underground for hundreds of millions of years. We burn them for warmth, for motion, for power. In doing so, we released carbon dioxide, methane, and other greenhouse gases into the air faster than Earth's systems could absorb them. The result? A warming planet. Glaciers retreat, oceans rise, storms intensify, fires grow fiercer, seasons shift, coral reefs bleach, and sea levels creep inland. Not in leaps, but in inches that add up. And it isn't just the air. Plastic, a miracle of chemistry, became the skeleton of modern convenience. Light, durable, mouldable, it revolutionized medicine, transportation and food safety. But it lingers, and a bottle thrown away today may outlive empires. Microplastics drift through oceans, into soil, into our bodies. They have been found in raindrops, in the deepest trenches of the sea, and in unborn children. Extinctions too are accelerating. Amphibians vanish before we learn their names. Insects disappear from fields that once buzzed with life. Great mammals, tigers, elephants, whales stand as survivors of a past world now cornered into shrinking habitats. The sixth mass extinction, as biologists call it, is not coming. It is here. And it is quieter than the last 5. Less a sudden impact, more a slow unravelling. Beneath this there is the hidden pressure. Food, water, soil. The systems that nourish 8 billion human lives are strained. Rivers are dammed, aquifers depleted. Soils, overworked and underfed, lose their richness. Crops face drought, disease, rising salt and changing seasons. Climate doesn't just warm, it destabilizes. And in the middle of this sits the human being, not evil, not separate, just complex. A creature capable of compassion and forgetfulness, of building wind farms and burning forests, of writing declarations of rights and laying pipelines through sacred land. Some call this the Anthropocene, a new epoch, defined not by ice or stone, but by us. Geologists debate the term, but even without agreement, the idea feels intuitively true. That the mark of our presence is now etched into sediment, into atmosphere, into species counts and extinction curves, into isotopes that will remain readable in rock long after we're gone. It is tempting in moments like this to reach for despair, but despair is a kind of surrender, and if this long journey has shown anything, it is that life rarely surrenders easily. We are not merely the problem, we are also the mirror. We can reflect, we can change course, we can plant forests, restore wetlands, remove carbon from air, clean rivers, protect species. We can vote with dollars and ballots, we can teach, we can remember. The Earth is not asking for perfection, it's asking for attention. And attention is something we're good at, when we choose to give it. We know how to collaborate. We've built global networks of knowledge. We've reduced child mortality. We've cured diseases. We've landed rovers on distant planets and mapped the genomes of tiny microbes. The same ingenuity that split atoms can knit ecosystems back together. The same minds that built factories can build resilience. And the same species that once huddled in caves now lights the night with wind, sun, and stars. Yes, there are limits. Yes, we've made mistakes. But there is something deeply hopeful in the very idea of noticing. Because to notice is to care. And to care is the beginning of healing. We live in an age where the tools of destruction and the tools of restoration are held in the same hands. And what we choose to do with them, that is the story still being written. This moment is not an end. It is a hinge, a pause between what we inherited and what we might leave behind. And while we cannot go back, we can go forward, more gently, more wisely, more together. That is the fragile beauty of now. Earth has been kind to us. It gave us water and warmth, seasons and soil, fire and stories. It held us through storms and time, fed our questions, echoed our songs, and gave us a sky we could never stop staring into. But even as we built homes and cities, gardens and schools, a part of us never stopped looking up. It may have begun as wonder, but now it is also necessity. We know that Earth, though vast to us, is not invincible. Its climate can shift. Its core may one day cool. Its oceans may slowly vanish. The sun, generous now, will grow brighter over time, expanding, consuming, changing. The physics of stars are not sentimental, so we ask, what comes next? For some, the answer lies in Mars. It is not friendly. Its air is thin, its soil dry, its nights colder than any we've known. But it has potential. Ice waits beneath its surface. Daylight matches our rhythms. It is close enough to reach. Perhaps not easily, not soon for most of us, but within the reach of science. Robotic scouts have already roamed its deserts. Rovers have found the memory of rivers, the whisper of possible life. Could we live there? Maybe not in forests, not yet, but in domes, in shelters, in thought. Further out lie Europa and Enceladus, icy moons with oceans beneath their frozen skin. They orbit giants, Jupiter and Saturn, but beneath their surfaces warmth seeps from tidal forces. Water moves. Life, if it exists there, would be alien in every sense. But if it doesn't, we might still send it. Because our ambition is not only to survive, it is to spread, to scatter seeds, biological or digital, to leave echoes, instructions, fragments of memory in orbit around stars that will outlive our sun. Some imagine a future not of people, but of machines, explorers shaped from silicon and thought, able to endure radiation, time and void. Already, artificial intelligence makes decisions in microseconds, navigates spacecraft, simulates weather. It may one day evolve into something not like us, but born of us. Others look to synthetic biology, where genes can be edited, cells rewritten, life redesigned. Perhaps we won't send humans to distant planets. Perhaps we'll send life built to survive there. Organisms engineered to breathe alien air, to glow in darkness, to bloom in sulphurous soil, and some imagine both. Futures where mind is no longer bound to carbon or neurons, where consciousness might one day migrate into digital forms, not to escape the body, but to extend its reach. Mind as signal, memory as architecture. These are not certainties, they are possibilities, and like all stories of the future, they carry both hope and caution. Because what we carry with us, our curiosity, our creativity, our capacity for wonder, is not always gentle. We've changed this planet, sometimes without knowing, sometimes without caring. If we go to other worlds, we must go not as conquerors, but as learners, as guests in the universe's long, quiet song, and perhaps in all this we will not be alone. The question of life beyond Earth is still open. We listen for signals, we scan planets, we search for the chemistry of breath and the geometry of metabolism. So far we've heard only silence, but silence is not the same as absence. The universe is wide and light takes time. Even if we are the only ones here now, we may not always be. Perhaps life is rare. Perhaps intelligence is rare. Or perhaps civilizations flare and fade too quickly, like candles in wind. But the search itself changes us. It reminds us of how much we do not know, and how much we still might. Whether we stay or go, whether we flourish or flicker, what matters most may not be scale. It may be intention. To build kindly, to question wisely, to wonder often. Because even if humanity one day vanishes, even if Earth returns to silence, our presence can still mean something, in a signal left behind. In an AI archive drifting between stars, in the genes of a moss we seeded on Mars, in a poem etched on titanium and hurled beyond Pluto. We may not live forever, but meaning can outlast matter. And so, this story does not end with extinction or certainty. It ends with open hands. The same hands that once chipped flint tools now guide spacecraft. The same minds that told myths beneath constellations now simulate universes. The same hearts that fear the dark still reach for distant suns. And wherever we go, whether into space, into machines, into silence, we take with us the memory of oceans, of wind in trees, of voices rising together. We take Earth with us, always. The Earth was never guaranteed. There was no law that said a planet like this must exist. No equation that demanded oceans, forests, fireflies. No commandment in physics that required a moon the right size, or a tilt that creates seasons, or a field that shields from solar wind. It didn't have to happen, and yet it did. Out of all the patterns of dust and gravity, all the collisions and coolings, all the wild uncertainties of deep time, something stable and strange emerged. A quiet blue dot that floats, fragile and stubborn, in the dark. A home. Not perfect, not permanent, but deeply, undeniably alive. It began in fire, in magma and impact, in heat that hummed beneath the crust. Oceans arrived with ice and vapour. Continents wandered like drifting thoughts. Lightning cracked the sky. Simple molecules wove themselves into new shapes. And somehow, someway, those shapes remembered how to make more of themselves. They became cells, and cells became colonies, and colonies became coral reefs and trees and dragonflies. They became dinosaurs and birds and forests of singing insects. They became mammals who raised their young in warmth, and primates who looked not just at trees but beyond them. And then, after so much waiting, after so many extinctions and experiments, they became us. We are not separate from this story. We are its continuation. We are the product of erosion and explosion, of mutation and memory. We are the thunder in bones, the breath of leaves, the story the earth tells itself in moments of consciousness. We carry its elements in our veins, iron from old stars, salt from ancient seas, calcium from crushed shells. We carry its past in our DNA, echoes of fish and fur, of wings that failed and dreams that flew. We carry its future in our choices, in the care we offer, the harm we undo, the beauty we build and leave behind. Even our imagination is geological. We build monuments out of thought, cities out of shared myth, technology out of remembered stone. Our metaphors are rivers, branches, mountains. Our rhythms echo the tides. Even our sleep follows the spin of this old world beneath us. And through it all the earth has held us. It has cracked and quaked. Yes, it has flooded and burned. But it has also warmed us, fed us, offered sunsets and seeds, wind for our kites and water for our poems. It has given us a stage for every love, every heartbreak, every lullaby, every invention, every birth. All that you are, all that anyone has ever been, has happened on this small rock with its soft blue skin, and maybe, just maybe, one day we'll leave. We might walk on red dust beneath alien suns. We might carve domes into frozen moons. We might send our thoughts through machines that drift for centuries, carrying memory into the dark. If we do, we'll go not as strangers to the cosmos, but as children of Earth, bringing with us its warmth, its mistakes, its questions, and its songs. We'll carry the memory of rain, of forests in autumn, of the sound of wind through wheat, of dogs dreaming in sunlight, of laughter in kitchens, of thunder over deserts, of waves meeting cliffs and the hush that follows. We'll carry the idea of home, not as a place, but as a feeling. Because Earth is not just where we live, it's what taught us how to. It taught us to grow, to grieve, to forgive. It taught us to name things, to share food, to build fires and stories and tools. It taught us patience when seasons were long. It taught us curiosity when stars refused to answer. It taught us reverence when silence felt sacred. It gave us everything, and still it asks only that we notice. That we notice the frost on a window, the curve of a mountain, the flicker of a moth's wing near a candle. That we notice each other, the quiet kindness of a shared moment, the miracle of understanding across time and distance. You, listening now, are a part of this long unfolding. You are the dust of stars rearranged to wonder. You're the voice of oceans trying to speak. You're the whisper of roots beneath pavement, still remembering the forest. You're very old and just beginning. So sleep now. Let your breath settle. Let your thoughts grow quiet. There is no hurry, no destination left tonight. You are where you need to be. The story continues, but for now, let it pass gently beside you, like a river in dusk, like wind over tall grass, like pages turning in a book you've almost finished, but not quite. You are home, and Earth, strange and beautiful Earth, is still here, spinning beneath you, singing in a voice too deep to hear, but always there. Thank you for walking through this story. Thank you for being part of this world. Sleep well, dear traveller.